The 190,000 year gap in human behavior. Here's a question that sounds simple but isn't. When did we become human? Not when did humans appear. That's easy. Bones can tell us that. But when did we become the kind of human that matters? The kind that makes art and buries the dead with flowers. The kind that looks at stars and wonders why. Because here's the thing, modern humans showed up about 300,000 years ago. We know this from skulls found in Morocco. High foreheads, small faces, chins. These people looked exactly like us. Their brains were the same size as ours, same structure, same capacity. But for 190,000 years, they left almost nothing behind. No cave paintings, no jewelry, no burial sites that suggest they cared about death, no evidence of trade networks or complex tools, nothing that screams humanity the way we understand it. The brains were there. The hardware was installed, but something else was missing. Then around 70,000 years ago, everything changed. Suddenly there's art. Suddenly there's culture. Suddenly, humans are making beads and carving figurines and painting on cave walls. They're burying their dead with care. They're trading shells across hundreds of miles. They're acting human. What happened? Some scientists think it was a mutation, one small genetic change that flipped a switch in the human brain. A random accident that made us who we are. Others say no. The capacity was always there. Culture just takes time to develop. It spreads slowly. It needs the right conditions. Nobody knows for sure. But think about this. For 190,000 years, humans walked around with brains capable of Shakespeare and quantum physics. They had the mental tools to build rockets and write symphonies. But they didn't. They just survived, made simple tools, hunted, gathered, lived, and died. Were they less human than us? Or were they human in a way we can't quite understand anymore? This is the mystery we're going to explore. The gap between having a human brain and being truly humans. The RB after BRB RB 40 at was be the moment when something shifted inside us, when we stopped just surviving and started creating meaning. It's a story about evolution, but not the kind you learned in school. Not about bodies changing over millions of years. This is about minds, about consciousness, about the strange accident that might have made us who we are. And here's what makes it perfect for tonight. There are no clear answers, just possibilities, just theories floating in the dark. The kind of mystery you can sink into, let your mind wander through, drift with. So settle in, get comfortable. We're going back to a time before art existed, before anyone had buried their dead or wondered about tomorrow. Back to humans who had all the pieces but hadn't quite put them together yet. Back to the moment before we became us. If this video is helping you slow down or fall asleep, that's the whole idea. Subscribe if you'd like and let me know where in the world you are and what time it is. I genuinely love seeing that. So, where did we come from? Not humans. We already know humans appeared 300,000 years ago. But where did those humans come from? What did our ancestors look like before they became us? The answer takes us back 6 million years to a creature that wasn't quite human and wasn't quite ape. Something in between. Scientists call this the last common ancestor, the species that split into two branches. One branch became chimpanzees, the other became us. We've never found its bones. Probably never will. Fossils are rare. Most creatures die and rot and disappear. The odds of becoming a fossil are astronomically small. You need the right conditions, the right soil, the right timing. Most of our ancestors left no trace at all. But we know this creature existed because here we are, and there are chimps, and we share 98.8% of our DNA. That tiny difference, that 1.2%, 2%, that's what made us human. Think about how small that is. Take your genome, all 3 billion base pairs, change just 36 million of them. That's the difference between you and a chimpanzee. 36 million sounds like a lot, but spread across 3 billion, it's nothing, a rounding error, a handful of typos in a library of books. And yet those typos changed everything. The last common ancestor probably looked more like a chimp than a human. Covered in hair, long arms, built for climbing, it lived in the forests of Africa. Ate fruit mostly, maybe some leaves, some insects. Its brain was about the size of a modern chimp's brain, around 400 centimeters. A human brain today is 1,400 centimeters, more than 3 times bigger. But size isn't everything. Elephants have brains 4 times bigger than ours. Whales have brains 5 times bigger. They're not writing poetry or building rockets. What matters is structure, organization, how the brain is wired. The last common ancestor had a brain that could solve problems. It could use tools. Chimps today use sticks to fish. For termites, they use rocks to crack nuts. They plan ahead. They remember. They recognize themselves in mirrors. That's sophisticated, that's smart. But it's not human smart. The difference is subtle but profound. A chimp can use a stick to get termites. A human can look at a stick and imagine a spear, a ladder, a bridge, a symbol, a god. Somewhere between that common ancestor and us, something changed in the brain. Not just size, not just raw processing power. Something about how we think. Scientists call it symbolic thought, the ability to let one thing represent another thing, to see meaning beyond the physical, to create abstractions. This is what makes language possible. A sound represents an object. A word represents an idea. A story represents truth. This is what makes art possible. A line on a cave wall represents a bison. Red ochre represents a bison. Red ochre represents a person who died. This is what makes religion possible. A tree represents life. A mountain represents heaven. Ritual represents connection to something beyond yourself. The last common ancestor couldn't do this. Its brain was concrete, literal. It saw a stick and thought stick, food and thought, food, threat and thought, food, threat and thought, run. It lived entirely in the present moment. No past, no future, just now. And honestly, there's something beautiful about that. Something we've lost, that total presence, that complete absorption in the immediate. But it also meant no planning beyond tomorrow. No stories about where you came from. No wondering about what happens after death. No art, no culture, no meaning beyond survival. The split happened around 6 million years ago, maybe in East Africa. Maybe when the climate changed and forest became grasslands. Maybe when some group of these creatures got cut off from the others. Separated by a river or a mountain range or just distance. Evolution needs separation. If populations keep mixing, genes keep blending, nothing new emerges. But separate them, let them adapt to different environments. Now you get change. One population stayed in the forests, kept climbing trees, kept eating fruit. These became chimpanzees and bonobos. The other population moved to the grasslands, started walking upright, started eating different food. These became us, but it took time, millions of years. The change was so gradual that no single generation would have noticed. Your parents looked like you. Your children looked like you. But your ancestors from 100,000 generations back, they'd look alien. The first major change was walking upright. This freed up the bad. Hands, suddenly you could see. Things, make things, use tools while walking. But walking upright came with costs. It's harder on the spine, harder on the keys. Childbirth became dangerous because the pelvis had to narrow to support upright walking. Human babies are born helpless because they have to be born early, before their heads get too big to fit through that narrowed pelvis. Evolution doesn't care about comfort, it cares about survival. And apparently, walking upright helped enough that it was worth the back pain and the difficult births. The second major change was diet. Moving to the grasslands meant less fruit, more meat, more tubers and roots that require digging. Meat is dense nutrition. It provides protein and fat and calories in the sage. It provides protein and fat and calories in compact package, but it requires hunting or scavenging or both. Our ancestors probably started as scavengers, following predators, waiting for them to finish eating, then moving in to crack open the bones for marrow. Marrow is rich in fat. Other animals couldn't get to it, but if you had a rock, you could smash the bone open, access nutrition nobody else could reach. This is tool use, basic, simple, but it's a start. The third major change was the brain. It started growing slowly at first, then faster. Nobody knows exactly why. Maybe meat provided the nutrition needed for a bigger brain. Brains are expensive. They use 20% of your calories, despite being only 2% of your body weight. You need dense nutrition to support that. Maybe social complexity drove it. Living in groups requires keeping track of relationships. Who's allied with whom? Who owes favors? Who can be trusted? This requires memory and planning and theory of mind. Maybe it was tool making. Creating tools requires imagining something that doesn't exist yet, planning steps, remembering techniques, teaching others. This requires abstract thought. Probably it was all of these things. Evolution rare, lie has one cause. It's always multiple pressures, pushing in the same direction. By 2 million years ago, our ancestors had brains twice the size of chimps. They were making sophisticated stone tools, hand axes, that required planning and skill. These hand axes are remarkable. Teardrop-shaped, flaked on both sides, symmetrical, beautiful even. And they didn't change. For 1.6 million years, humans made the same hand axes generation after generation. The exact same design. Think about that. 1.66 million years of tradition, of teaching children the way your parents taught you of perfection, through repetition. We can't imagine that kind of stability. Now we change everything constantly. New phones every year, new fashions every season, new ideas every day. But for most of human history, change was glacial. What worked kept working. Why mess with success? The hand axes worked. They cut meat, scraped hides, dug roots, chopped wood. They were the Swiss Army knife of the Stone Age. And because they worked, they didn't change. This tells us something about the minds that made them. They could plan, they could learn, they could teach, but they weren't innovating, weren't experimenting, weren't asking, what if? They had bigger brains than the common ancestor, but they weren't thinking like modern humans yet. That spark, that creative restlessness, that drive to make something new, it wasn't there yet. The hardware was being installed, the brain was growing, the capacity was developing. But the software, the cultural programming that makes us human, that was still loading. And it would take another million years before it finally booted up. Before someone looked at red ochre and saw not just dirt, but the possibility of meaning. Before someone carved a cap head, not because it was useful, but because it was beautiful. Before someone buried a body with flowers and wondered if there was some anything beyond this life. Before we became the kind of human that asks why. The last common ancestor gave us the foundation, the raw material, the biological inheritance. But something else had to happen. Some change, some mutation, some cultural shift, something that turned survival into meaning, that turned existence into story, that turned life into something worth wondering about. And when that happened, we stopped being just another ape. We became something new, something strange, something that could look back at its own ancestors and ask where it came from. We became human not in body, but in mind. There's something strange about that. We're separated by oceans and time zones, different languages, different lives. But we're all wondering about the same thing, where we came from, what made us human. And maybe that wondering is part of what makes us human in the first place. Anyway, back to the story. Here's the thing about standing up. It seems simple, but it changed everything. Around 7 million years ago, something happened in Africa. A branch of apes started spending more time upright. Not all the time, not even most of the time at first, but more than their cousins. They stood up to see over tall grass, to spot predators, to reach fruit in low branches, to carry things, and their bodies began to change. The spine curved into an S shape, the pelvis widened and tilted, the legs straightened and lengthened. The feet developed arches. The big toe moved in line with the others instead of sticking out to the side like a thumb. These changes took millions of years. They happened slowly, generation after generation, each small shift making the next one possible. By 4 million years ago, some of these apes walked upright most of the time. We call them Oropithecines, southern apes. Their fossils show bodies caught between two worlds, hips built for walking, arms still, low, long enough for climbing, feet that could grip branches, but also support their weight on flat ground. They lived in the trees and on the ground, the best of both worlds, or maybe the worst, not fully adapted to either, but they kept walking. Think about what walking upright costs. It's not efficient. 4 legs are better than 2 for speed, for stability, for carrying heavy loads. Chimpanzees can move through forests faster than humans. Gorillas are stronger. Baboons can climb and run and fight better than any upright ape could. So why did we keep doing it? The usual answer is that it freed our hands. And that's true, but it's not the whole story. Standing up made us vulnerable. Our guts hung exposed, no fur to protect them. Our throats were at the perfect height for a predator's jaws. We couldn't run as fast as 4-legged animals, couldn't climb as well as other apes. We gave up a lot to stand up, but here's what we gained. First, efficiency. Walking upright uses less energy than knuckle walking. Not much less, but enough in a world where food was scarce, where you might walk 10 miles a day looking for something to eat. That difference mattered. You could travel farther on the same amount of food, cover more ground, find more resources. And in the African savanna, where food was spread out and seasonal, that was huge. Second, thermoregulation. That's a fancy word for temperature control. When you stand upright, less of your body is exposed to the sun. Your head is higher up where there's more breeze. You can walk in the heat of the day, when other animals have to rest. That gave early humans a weird advantage. We could hunt by just following animals until they collapse from heat exhaustion. We call it persistence hunting. It sounds ridiculous, but it worked. Third, visibility. Standing up let you see farther over grass, over bushes. You can spot predators earlier, see where other animals are gathering, notice changes in the landscape. In open country, height equals information. Information equals survival. But fourth, and this is the big one, standing up freed our hands, not just to carry things, not just to make tools. Those came later. First, it freed our hands to do nothing. Think about that. A chimpanzee's hands are always busy holding branches, supporting weight, knuckle walking, climbing. Their hands are tools for movement. Our hands became available, empty, ready. And once your hands are free, you can start using them for other things. You can gesture, point, show someone something. You can carry food back, to share. You can hold a baby while you walk. You can pick up a stick and use it as a weapon. You can make things. The first stone tools appear in the fossil record around 3.3 million years ago. Simple flakes, rocks deliberately broken to create sharp edges. Nothing fancy, but they worked. These tools show up before the genus Homo, before big brains. Oralopathes probably made them, or something like Oralopathes probably made them, or something like Oralopathes, bright apes with small brains and free hands. The tools didn't require much. Where we came from, the last common ancestor, 6 million years ago, intelligence to make. You bash one rock against another. Flakes break off. Some are sharp. You use the sharp ones. But here's what's interesting. Making these tools requires something specific. You need to be able to hold one rock steady while hitting it with another. You need precision, control, the ability to adjust your grip and angle. You need hands that aren't designed for climbing anymore. Hands that have short fingers and long thumbs. Hands that can grip things tightly and manipulate them carefully. You need human hands. The fossil record shows this happening around 2 million years ago. Hand bones start changing. The thumb gets longer and stronger. The hinge. Wrist gets shorter. The wrist bones rearrange to allow better rotation. These changes made tool making easier, but they made climbing harder. The same adaptations that let you grip a stone tool precisely make it harder to grip a tree branch. Evolution was making a choice. Tools over trees, ground over canopy. A new way of living. And once you commit to that, once your body is built for walking and your hands are built for making, you can't go back. You're stuck on the ground, vulnerable, slow, weak compared to other predators. You'd better be smart enough to make it work. Standing up also changed how we give birth. This part is important. The pelvis had to do 2 things at once. Support upright walking. Allow babies to pass through during birth. These 2 requirements fight each other. Walking upright works best with a narrow pelvis. Birth works best with a wide one. Evolution had to compromise. The compromise was this. Human babies are born earlier in development than other apes, more helpless, less able to survive on their own. A baby chimpanzee can cling to its mother's fur within hours. A human baby can't even hold up its own head. We're born premature by ape standards. 3 months too early. Some scientists say, if we gestated, as long as we should, pregnancy would last a year. But we can't. The baby's head gets too big. The pelvis can open wide enough. So we're born early, helpless, dependent. This created a problem. A human baby needs constant care for months, years, really. You can't just put it down and go find food. It'll die. So someone has to carry it, feed it, protect it all the time. This probably pushed early humans toward more cooperation, toward sharing food, toward helping each other raise children. You can't raise a human baby alone. Not easily. You need help. Maybe that's where community started. Not from intelligence, not from language, but from the fact that our babies were too helpless to survive without constant group support. Standing up made us social, not by choice, by necessity. The energy cost of big brains came later, but the energy cost of helpless infants came right away. A mother nursing a human baby needs more calories than a mother nursing a chimp baby. The baby nurses longer, needs more care, takes more time. That food has to come from somewhere, probably from other people, fathers, grandmothers, siblings, the group. So standing up didn't just free our hands, it bound us together. There's something else standing up did. It changed how we see the world. Literally, when you're on all fours, you look down. Your eyes scan the ground right in front of you. Your field of vision is narrow, focused on the immediate. When you stand up, you look out. Your eyes are higher. Your field of vision expands. You see the horizon, the distance, the big picture. This might breaks, the story stops. This might sound like philosophy, but it's anatomy. Your eye position determines what you pay attention to, what you think about, how you understand space and time. Standing up made us think differently, not smarter, just different, more aware of distance, of future, of things that aren't right in front of us. Maybe that's where planning started. The ability to think about tomorrow, next week, next season. You can see farther. So, you start thinking farther. The fossil record shows all this happening slowly, very slowly. The first upright apes appear 7 million years ago. The first stone tools appear 3.3 million years ago. The first big increase in brain size appears 2 million years ago. 4 million years between standing up and getting smart. 4 million years of just walking around with free hands and small brains. What were we doing all that time? Probably just surviving, walking, making simple tools, eating, raising helpless babies, cooperating because we had to, not thinking about the future, not making art, not wondering about the stars, just living. But the foundation was there, the hardware, upright bodies, free hands, social groups, helpless babies that forced us to work together. We had the physical setup for intelligence. We just hadn't figured out how to use it yet. That would take another 2 million years. And even then, as we've seen, having the hardware doesn't mean you'll use it. Modern humans existed for 190,000 years before creating culture. But standing up was the first step, the foundation, the thing that made everything else possible. It seems simple, just standing up. But it cost us our speed, our climbing ability, our easy births, our independence. And it gave us free hands, social bonds, a different way of seeing the physical foundation for intelligence. Whether that was a good trade, we're still figuring out, but we're stuck with it now. We can't go back. Our bodies are committed, built for walking, for carrying, for making things. For better or worse, we're the apes who stood up, and that choice made millions of years ago by creatures who couldn't imagine where it would lead determines everything about how we live now. Every step you take, everything you hold, every thought you think, all of it traces back to that first ape who spent a little more time upright, who freed their hands, who saw a little farther, who took the first step toward being human. Here's what free hands actually meant. Not just freedom, capability. Once you're standing upright, most of the time, your hands stop being feet. They become something else. Tools for manipulation, for precision, for making things. The earliest stone tools we found are 3.3 million years old. They come from a site in Kenya called Lamechi. 3 simple flakes, rocks deliberately broken to create sharp edges. Nothing fancy. You take one rock, you hit it with another rock, pieces break off. Some pieces are sharp. You keep the sharp ones. That's it. That's the whole technology. But here's what's interesting. These tools appear before the genus Homo, before big brains. Something with a brain the size of a chimpanzee's made them. Australopithecines, probably, or something like them. Small-brained apes who walked upright and had free hands. The tools themselves are crude, rough, irregular, but they worked, they cut, they scraped, they smashed. That was enough. For almost 2 million years, that was enough. Think about that timeline. Stone tools appear 3.3 million years ago. The next major innovation doesn't show up until 1.76 million years ago. That's 1.5 million years of making basically the same thing, the same rough flakes, the same simple technique, generation after generation, for longer than modern humans have existed. Why didn't the tools improve? Why didn't someone figure out a better way? Maybe because they didn't need to. The tools worked. They solved the problems early humans faced. Cut meat, scrape hides, break bones to get at marrow, process plants. If it works, why change it? But around 1.76 million years ago, something did change. A new type of tool appears. We call it the Ullyan hand axe. These are different, not just sharp flakes. Deliberately shaped stones, teardrop-shaped, flaked on both sides to create a symmetrical form, sharp edges all around. They took skill to make. Planning. You couldn't just bash two rocks together. You had to think about the shape, remove flakes in the right order, create a form that existed in your mind before it existed in the stone. This required something new, not just free hands, but hands that could execute complex sequences. Brains that could plan multiple steps ahead, eyes that could judge angles and edges. The hand axe shows up right when the genus Homo appears, right when brains, eyes, starts increasing. That's not a coincidence. Bigger brains meant better tools. Better tools meant more food. More food meant bigger brains could survive. A feedback loop, each advance making the next one possible. But here's the strange part. Once the hand axe appeared, it didn't change much either. The basic design stayed the same for 1.5 million years. 1.5 million years, the same teardrop shape, the same technique. From Africa to Europe to Asia, everywhere humans went, they made hand axes. The same hand axes. You could take a hand axe from 1.7 million years ago and one from 200,000 years ago and barely tell them apart. Different rocks, same shape, same method. This is what archaeologists call the industry. It's the longest-lasting technology in human history. Nothing else comes close. Not fire, not agriculture, not writing, nothing. The hand axe worked, so it stayed. What did people do with these tools? Everything. They were the Swiss Army knife of the Stone Age. Cut meat. Absolutely. A hand axe could butcher an entire elephant. Slice through hide, separate joints, cut away meat from bone, scrape hides. The sharp edge could remove fat and tissue from animal skins, make them flexible, prepare them for use as clothing or shelter. Dig. The pointed end could break ground, dig up roots, excavate tubers, get at underground food sources, chop wood, sharpen sticks, make other tools. A hand axe could shape wood into spears, digging sticks, clubs. They were general-purpose tools, not specialized, not optimized for one task. Good enough for one task, good enough for everything. And maybe that's why they didn't change. Specialization comes later. When you have enough people, enough stability, enough surplus. Early humans didn't have that. They needed tools that could do anything. The hand axe could do anything. But making one required something specific, a particular kind of hand, a particular kind of bra. Look at your hand right now, your thumb. It's long, it reaches past the first knuckle of your index finger. It can rotate, press against each finger individually. Create a precision grip. Chimpanzees can't do this. Their thumbs are shorter, less mobile. They can grip things, but not with precision, not with fine control. Human hands evolved for tool making. The thumb got longer. The fingers got shorter. The muscles that control fine movements got stronger. The wrist bones rearranged to allow better rotation and manipulation. These changes show up in the fossil record around 2 million years ago, right when hand axes appear. The hardware and software evolving together, but hands alone aren't enough. You need eyes. Specifically, you need hand-eye coordination. Making a hand axe requires you to hit a stone at exactly the right angle, with exactly the right force, while holding it steady, while adjusting your grip while rotating the stone to work on different edges. You're coordinating vision, touch, motor control, spatial reasoning, and planning all at once, in real time. This requires brain power, not just size. Connectivity. The visual cortex talking to the motor cortex, the planning regions coordinating with the sensory regions. The brain had to rewire itself to make tools, new connections, new pathways, new ways of processing information. And once you have that ability, once your brain can coordinate complex hand movements based on visual feedback, you can do other things too. You can gesture, point, show someone something, use your hands to communicate. You can manipulate objects in new ways, stack things, arrange things, build things. You can teach, show someone else how to make a tool, demonstrate technique, pass on knowledge. Tools didn't just require smart hands. They created opportunities for smart hands to do more. But here's what's missing from this picture. Cult. Europe here, hand axes appear 1.76 million years ago. They spread everywhere humans went. They stayed the same for 1.5 million years. But there's no evidence of culture, no art, no decoration, no symbolism. The hand axes are purely functional. No one carved patterns into them. No one made them beautiful. No one signed their work. They're identical everywhere for 1.5 million years. That tells you something. The people making them could plan, could coordinate complex movements, could pass on techniques, but they weren't thinking symbolically, weren't expressing themselves, weren't creating meaning beyond function. The artware was there, the hands, the coordination, the basic intelligence. But something else was missing. The spark. The thing that makes us human. Tools show up in other species too. Chimpanzees use sticks to fish for termites. Crows use hooks to get food. Sea otters use rocks to break open shells. But those tools are simple. Found objects, barely modified, used once and discarded. Human tools are different. Made, shaped, carried, kept passed down, improved over generations. That's what makes them human, not just using objects, making them deliberately with intention. The Lamaki tools from 3.3 million years ago show intention. Someone looked at a rock and saw potential, saw something that could be weed, then made it real. That's a cognitive leap. Not huge, but real. From using what exists to creating what doesn't. The hand axe is a bigger leap. Someone looked at a rock and saw a specific shape, a teardrop, symmetrical, sharp, all around, then removed everything that wasn't that shape. They held an image in their mind, a goal, then worked toward it step by step, flake by flake. That requires imagination, the ability to see what isn't there yet, to hold an idea and work toward it. But it's not symbolic imagination. Not yet. The hand axe is still just a tool. It doesn't represent anything. It doesn't mean anything beyond its function. It's practical imagination, concrete, tied to immediate needs. The leap to symbolic thinking comes much later. After language, probably after brains get even bigger, after something else changes that we still don't fully understand. But tools were part of the foundation. They showed that humans could imagine, could plan, could create. They just weren't imagining the right things yet. There's another aspect of tools that matters: social learning. You can't learn to make a hand axe by yourself. Not really. You could figure it out eventually. Trial and error. But it would take forever. It's much easier if someone shows you, demonstrates, lets you watch, corrects your mistakes. This means early humans had to have some form of teaching, some way of passing on knowledge, not language necessarily, but something: demonstration, imitation, feedback. Archaeological experiments show this. Modern humans trying to learn stone tool making without instruction struggle. They can do it, but it takes months, years even. With instruction, you can learn the basics in hours, days, for more complex tools. Early humans probably learned the same way. By watching, by trying, by being corrected, by the brain that changed everything. From 400cc to 1/400cc practicing. This created culture, not symbolic culture, not art or ritual, but practical culture, shared knowledge, techniques passed down, a body of information that existed outside any individual brain. The Handex design spread across 3 continents that required transmission, teaching, learning, copying. It required social bonds, groups stable enough to allow learning, relationships that lasted long enough to pass on skills. Tools made us social, not because we wanted to be, but because we had to be. You can't maintain complex tool traditions without social learning, without grow-ups, without teaching. The tools themselves are evidence of society. By 500,000 years ago, tools start getting more specialized, different shapes for different tasks. Scrapers, points, blades, cleavers. This shows increasing sophistication, better understanding of materials, better planning, better teaching, but still no art, no decoration, no symbolism, just function. Better function, more specialized function, but still just function. The hardware keeps improving, the hands, the eyes, the coordination, the social learning, but the software isn't there yet. The cultural explosion, the symbolic thinking, the thing that makes us truly human, that's still hundreds of thousands of years away. Tools show us what early humans could do: plan, create, teach, learn, work together. But they also show us what early humans couldn't do. Imagine beyond function, create meaning, express themselves and symbolically. They had the hands, they had the coordination, they had the basic intelligence. They could make things, complex things, useful things. But they couldn't yet make meaning. That would require something else, something that wouldn't appear until much, much later. But the foundation was there, in the hands, in the tools, in the social learning required to pass them on. Every hand axe was practice, every flake removed was training, every technique passed down was building toward something, building toward the moment when humans would finally use their hands, not just to make tools, but to make art. Here's the thing about meat: it changed everything, not just because it was food, because of what it took to get it, what it took to prepare it, what it took to eat it. Early humans didn't hunt at first. They scavenged, found dead animals, chased away smaller predators, took what they could get: a dead antelope, a zebra killed by lions, whatever was left after the real hunters finished. This was dangerous work. Lions don't like sharing, hyenas fight back, vultures remember your face, but the reward was worth it. Meat has calories, lots of them. Fat has even more. A single carcass could feed a group for days. The problem was getting to the good parts, the parts other scavengers couldn't reach. Big cats eat the organs first: the liver, the heart, the soft tissues, then the muscle meat. They leave the bones, the skull, the parts they can't easily access. Early humans figured out a trick. They could break bones with rocks, with tools. Inside the bones was marrow, pure fat, incredibly calorie-dense, and the big predators couldn't get to it. Their teeth couldn't crack the thick bones of large animals, but a rock could. A hand axe could. A deliberate strike in the right place. The bone splits open. The marrow is inside. Soft, rich, yours. This is what tools were really for. Not making other tools, not building things, getting calories, getting the food that other animals couldn't reach. The skull was even better. The brain inside is fatty, nutritious, protected by thick bone that predators can't penetrate, but humans could. With tools, with technique, with persistence, they became specialists in the leftovers. The parts nobody else wanted, the parts nobody else could access. This strategy worked. It worked so well that humans spread, followed the herds, followed the predators, followed the pewed. But scavenging has limits. You're always second, always waiting, always hoping something dies nearby. Hunting is better. You choose the target, you choose the timing, you control the outcome. The problem is that humans are terrible hunters physically. We're not fast. A human can't outrun anything worth eating. We're not strong. We can't overpower large prey. We don't have claws. We don't have big teeth. We don't have venom. What we have is endurance. We can walk, what for? Rever, run for hours, keep going when other animals collapse. This led to a hunting strategy that sounds insane. Persistence hunting. You find an animal, you chase it. It runs away, fast. You follow slowly, steadily. The animal stops, rests, catches its breath. You keep coming. It runs again. You follow, It stops. You follow. It runs. You follow. For hours in the heat, in the sun, you just keep coming. Eventually, the animal can't cool down, can't rest long enough, can't rest long enough, can't escape. It overheats, collapses, dies. Then you walk up and kill it with a rock, with a spear, with whatever you have. This works because humans can sweat. We can cool down while moving. Most animals can't. They have to stop, pant, rest. We don't. We just keep going. This hunting method requires tools, not for killing, for tracking, for carrying, water, for cutting meat afterward, You need containers, bags, something to carry water for the long chase. Early humans probably used ostrich eggs, gourds, animal bladders. You need cutting tools to butcher the kill, to carry meat back, to share the group. You need weapons eventually, spears, pointed sticks, something to finish the job. But the real tool is your body, your legs, your sweat glands, your brain planning the route, predicting where the animal will go. Hunting changed the social structure. You can't persistence hunt alone. You need partners, people to help track, to help carry, to help with the kill. You need cooperation, communication, trust. The meat gets shared, not equally, but shared. The hunters eat first, then the helpers, then everyone else. This creates obligations, debts, relationships. If you help me hunt today, I'll help you tomorrow. Social bonds form around meat, around hunting, around the shared effort and shared reward. But here's where it gets really interesting. Cooking. Nobody knows exactly when humans started cooking. The evidence is hard to find. Fire leaves traces, but controlled fire is different from wildfire. Cooking fire is different from warming fire. The earliest definite evidence of controlled fire is about 400,000 years old from a site in Israel. Kesem cave hearths, burned bones, repeated use of the same spots. But fire might be much older. Some researchers claim evidence going back 1.5 million years. Others are skeptical. The evidence is ambiguous. It could be natural fire, could be accidental. What matters is that at some point, humans started cooking and cooking changed everything. Raw meat is hard to digest. It's tough, chewy. Your stomach has to work hard to break it down. You spend a lot of energy digesting. Cooked meat is different. The heat breaks down proteins, denatures them, makes them easier to digest. Your body gets more calories for less effort. The same is true for plants. Raw tubers are hard, fibrous, difficult to chew and digest. Cooked tubers are soft, easy. Your body can extract the calories efficiently. Cooking is essentially pre-digestion. You're using fire to do work your stomach would otherwise have to do. This means more calories, more energy, more fuel for your body. And humans needed fuel because something was happening to their brains. Brain tissue is expensive. It burns calories constantly. Your brain is about 2% of your body weight, but uses 20% of your calories. Just sitting there just thinking, bigger brains need more fuel. A lot more fuel. You can't support a big brain on a raw food diet. There aren't enough hours in the day to eat that much. Chimpanzees spend about day 6 hours a day chewing. Gorillas spend even more. They're constantly eating, constantly processing food. Humans don't. We spend maybe an hour eating maybe 2 if we're feasting. The difference is cooking. Cooked food gives us more calories in less time, frees up time for other things. Was us to be bigger, hungrier brains. There's a researcher named Richard Wrangham who argues that cooking made us human, that controlled fire was the key innovation, the thing that allowed brain size to explode. He points out that human guts are small, smaller than you'd expect for a primate our size. We have short digestive tracts, small stomachs, small colons. This only makes sense if our food is pre-processed, pre-digested, cooked. Other researchers disagree. They point out that brain size started increasing before the earliest definite evidence of cooking. That meat alone might explain it. But everyone agrees cooking helped, made things easier, more efficient, more reliable. Cooking also changed social life. You can't cook alone. Well, you can, but it's inefficient. Fire takes work to maintain. You need fuel, someone to gather wood, someone to keep it going. Cooking takes time. You can't just grab food and eat. You have to prepare it, wait for it, tend it. This creates gathering points, places where people come together. Around the fire, around the food, stories get told, information gets shared, relationships form. The fire becomes the center of social life. Even today we gather around fire, around stoves, around grills. It's deep, bi-instinctive, ancient, but cooking did something else too. It created roles, division of labor. Someone gathers plants, someone hunts, someone maintains the fire, someone prepares the food, someone watches the children. Not everyone does everything. People specialize, get good at specific tasks, contribute in different ways. This requires coordination, planning, communication. Trust that everyone will do their part. Create interdependence. You need the group needs you. Nobody survives alone. Meat and cooking together created a feedback loop. More meat meant more calories. More calories supported bigger brains. Bigger brains meant better hunting. Better hunting meant more meat. Cooking amplified this, made the calories more accessible, made the brains even bigger, made the hunting even better. By 500,000 years ago, human brains were approaching modern size. Not quite there, but close. Much bigger than earlier humans. Much bigger than any other primate. This brain growth came at a cost. Human babies are born helpless, more helpless than other primates, because their brains are so big. A baby's head barely fits through the birth canal. Any bigger and birth would be impossible. So, humans are born early, underdeveloped, vulnerable. They need care, constant care for years. They can't cling to their mothers like other primates. Can't move on their own. Can't feed themselves. This creates another feedback loop. Helpless babies need more care. More care requires more cooperation. More cooperation requires better communication. More cooperation requires better communication. Better communication supports cultural learning. The whole system reinforces itself, each part making the others possible. Meat, cooking, tools, big brains, helpless babies, social cooperation, language, culture, all of it connected, all of it necessary. Remove one piece and the whole thing collapses. But there's still something missing from this picture. Something we haven't talked about yet. These humans with their big brains, their tools, their hunting, their cooking, their social cooperation, they still weren't us. Not quite. Not yet. They had the hardware, the brain size, the physical capability, the social structure, but the software wasn't there. The culture, the art, the symbolic thinking, the thing that makes us truly human. For hundreds of thousands of years, humans with modern-sized brains lived and died without creating anything we'd recognize as culture. No art, no decoration, no burial rituals, no jewelry, no cave paintings, nothing. The brains were there, the intelligence was there, the social cooperation was there. But something else was missing, something crucial, something we still don't fully understand. They could hunt, could cook, could make tools, could work together, could communicate well enough to coordinate complex activities, but they couldn't imagine, not symbolically, not abstractly, not in the way we do. They lived in the present, in the practical, in the concrete. They solved immediate problems, got food, stayed warm, raised children, but they didn't create meaning, didn't tell stories, didn't make art, didn't wonder about the stars, or maybe they did. Maybe they told stories around the fire. Maybe they wondered. Maybe they imagined. But if they did, they left no trace, no evidence, no mark on the world. The meat and the cooking gave them the energy, the calories to support big brains, the time to do more than just eat. But what they did with that time remains a mystery, a gap in the record, a silence that lasted hundreds of thousands of years. The stage was set, the pieces were in place, the brains were ready, something just needed to flip the switch. Turn on the light. Activate the potential that was waiting. That moment was coming, but it was still far off. Still tens of thousands of years away. In the meantime, humans ate, hunted, cooked, gathered around fires, raised children, made tools, worked together. They had everything they needed, everything except the spark, the thing that would finally make them us. The calories were flowing to their brains. All that energy, all that potential building, accumulating, waiting for something to happen, something that would change everything, something that would finally light the fuse. The brain explosion happened fast in evolutionary terms. Around 2 million years ago, early human brains were about 600 cubic centimeters, roughly the size of a chimpanzee brain maybe a bit bigger. By 1.5 million years ago, they'd grown to about 800 centimeters. That's a 30% increase in 500,000 years. By 500,000 years ago, human brains averaged 1,200 centimeters, getting close to modern size. By 200,000 years ago, they hit 1,400 centimeters, basically modern, the same size as yours right now. That's a journey from 600 to 1,400 in less than 2 million years, more than doubling in size, getting bigger, heavier, hungrier. This is weird, really weird. Brain growth this fast is almost unheard of in evolutionary history. Most animals evolve slowly, gradually. Small changes over millions of years, tiny adjustments, incremental shifts, but human brains exploded, shot up, ballooned like something was pushing them, pulling them, forcing them to grow. The question is, why? What was driving this? What advantage did big brains provide? The obvious answer is intelligence. Bigger brains meant smarter humans. Smarter humans survived better, had more children passed on their big brain genes. But it's not that simple. Brain size and intelligence don't match up perfectly, not even close. Neanderthals had bigger brains than modern humans, about 1,500 centimeters on average. But we don't think they were smarter than us, just different. Whales have huge brains, elephants too, but they're not building cities, not writing poetry, not launching rockets. Brain size matters, but it's not the whole story. Structure matters, organization, the way the parts connect, the density of neurons, the efficiency of processing. Still, human brains grew, and that growth required fuel. Lots of it. Here's where the meat and cooking come back in. They provided the calories, the energy budget, the fuel to run these expensive organs. But there's another piece, another cost that came with bigger brains, something that made the whole thing even more symbolic thought. The mutation that made us human complicated. Birth, human bee. Bees have big heads, huge heads relative to body size. Those big brains have to fit through the birth canal somehow. The problem is that humans also walk upright on two legs. This changes the shape of the pelvis, narrows it, makes the birth canal smaller, so you've got bigger heads trying to squeeze through a narrower opening. Something had to give. The solution evolution found was to birth babies early before their brains finished growing, while their skulls were still soft, still flexible. This works barely. Human birth is difficult, dangerous, more dangerous than for most other mammals, but it works. The cost is that human babies are born helpless, completely dependent, can't walk, can't cling, can't feed themselves, can't do anything. A newborn horse can walk within hours. A newborn deer can run within a day. A newborn chimpanzee can cling to its mother immediately. A human baby just lies there crying, needing constant care for months, years, a decade or more before it can truly survive on its own. This is called altriality, being born underdeveloped, helpless, requiring extended care. Most primates aren't this altrial. They're born more developed, more capable, more independent. But humans took it to an extreme. Our babies are the most helpless of all primates, maybe the most helpless of all mammals. This created a massive problem. How do you care for a helpless infant while also finding food, avoiding predators, surviving? You can't do it alone. Impossible. A mother with a newborn can't hunt, can't gather efficiently, can't move fast, can't fight. She needs help, support, protection, food brought to her, someone to watch the baby while she rests. This means cooperation, extended family, group living, social bonds that go beyond mating. Fathers had to stick around. Grandmothers had to help. Siblings had to contribute. The whole group had to invest in each baby. This is unusual. Most mammals don't do this. The mother handles it, maybe with some help from relatives, but not this level of group investment. Humans had no choice. The big brains demanded it. The helpless babies required it. The long childhood enforced it, and here's where it gets interesting. This created a feedback loop, a cycle that reinforced itself. Helpless babies need more care. More care requires better cooperation. Better cooperation requires better communication. Better cooperation requires better communication. Better communication requires bigger brains. Bigger brains make babies more helpless. Round and round, each generation slightly more dependent, slightly more social, slightly bigger. This is called the social brain hypothesis. The idea that brains grew to manage social complexity, to track relationships, remember obligations, predict behavior, navigate group dynamics. Living in groups is complicated. You need to remember who helped you, who owes you, who you can trust, who might betray you, who's allied with whom, who has power, who's vulnerable. This takes processing power, memory, theory of mind, the ability to imagine what others are thinking, planning, feeling, wanting. The bigger the group, the more complex the social web, the more you need to track, the more brain power required. Human groups got bigger, not huge but bigger than most primates, maybe 50 to 150 individuals, enough to need serious social intelligence. Some researchers think this is the main driver, that social complexity pushed brain growth more than anything else, more than tools, more than hunting, more than language. Others disagree, point out that other social animals don't have huge brains. That group living alone can't explain it. The truth is probably that everything worked together. Tools, meat, cooking, social, cooperation, communication, helpless babies, all of it. Remove any piece and the whole system might collapse. But together they created pressure, pushed brains bigger, made humans stranger, more dependent, more intelligent. But here's the really weird part, the part nobody fully understands. This brain growth happened in stages, in jumps, not smooth and gradual. Around 2 million years ago, there's a jump. Brains suddenly get bigger. This matches with the appearance of Homo erectus, the first truly human-like species, around 600,000 years ago. Another jump, brains grow again, approaching modern size. This is when fire use becomes more common. When hunting improves around 200,000 years ago, brains hit modern size. This is when Homo sapiens appears. When humans who looked exactly like us show up in the fossil record. But then something strange happens. The growth stops, levels off, stays at 1,410 cms. For 200,000 years, human brains don't get bigger. They actually get slightly, maybe smaller. Modern humans average about 1,350 cm, a bit less than early Homo sapiens. Why did growth stop? Why not keep going? Why not 2,000 centimeters, 3,000? One answer is cost. Brains are expensive. They burn calories constantly. About 20% of your total energy goes to your brain, just to keep it running. Bigger brains would cost more, require more food, more hunting, more gathering, more cooking, more time spent just getting enough to eat. There's a limit, a point where the costs outweigh the benefits, where bigger brains don't help enough to justify the extra calories. Humans might have hit that limit, found the sweet spot, the size that balances intelligence against cost. Another answer is birth. Babies' heads can't get much bigger. The pelvis can't get much wider without breaking the mechanics of walking upright. We're already at the edge. Birth is already difficult, dangerous. Any bigger and it might be impossible. So brain growth stopped, not because it couldn't continue, but because the constraints got too high. The cost too high, the risks too great. But the brains we have are impressive, packed with neurons, about 86 billion of them, each connected to thousands of others, creating trillions of connections, unimaginable complexity. The human brain has more neurons than any other primate, more connections, more processing power, more potential. But potential isn't the same as achievement. Having the hardware doesn't mean you'll use it. And for most of human history, that potential sat unused, waiting, dormant. Humans with modern-sized brains lived for 190,000 years without creating much of anything. No art, no culture, no symbolic thinking we can detect. They had the brains, the intelligence, the social cooperation, the communication. But something was missing. Some final piece, some spark that would ignite all that potential. The brain explosion gave humans the capacity, the hardware, the raw processing power. But capacity isn't destiny. You can have all the tools in the world and still build nothing. You can have all the ingredients and never cook. Something else had to happen. something to activate what was waiting to turn potential into reality. That moment was coming, but it was still far off, still tens of thousands of years away. In the meantime, humans lived, hunted, gathered, raised children, made tools, sat around fires, told stories that left no trace. Their brains were ready, fully formed, fully capable, fully modern, just waiting for the switch to flip, for the light to turn on, for the thing that would finally make them us. The explosion had happened. The brains were built. The stage was set. Now something just needed to walk onto it, to use what evolution had created to fulfill the promise of those 86 billion neurons. The hardware was complete. The software was still loading, still buffering, still waiting for the right moment to boot up. And when it finally did, everything would change. The world would never be the same. Humans would never be the same. But that's a different story, a different moment, a different mystery. For now, the brains were there. Big, expensive, hungry, powerful, ready. Just waiting. Waiting for someone to figure out what to do with them. Waiting for the moment when potential becomes reality, when capacity becomes creation. The explosion was over. The growth was done. The brains had reached their final size. What happened next would determine whether all that growth meant anything, whether those big brains would change the world or just consume calories for nothing. The answer was still hidden, still waiting, still decades of millennia away, but it was coming slowly, inevitably, like dawn after a long night. The brains were ready. The question was whether humans were. So we've got these big, powerful brains. The hardware is all there. But for almost 200,000 years, nothing much happens. No art, no jewelry, no written messages, no cave paintings, no little carved statues, just the same stone tools. Over and over again, the same simple shelters, the same way of life. It's as if humanity is standing at the starting line. All the potential is packed inside their heads. But nothing's really moving yet. Something needs to light the fuse. And here's where things get interesting, because scientists started looking for clues. DNA, fossils, tools, anything to help answer the question, what changed? Why did humans suddenly start acting so differently? The story leads us to a single gene. It's called FOXP2. Let's talk about genes for a second. Genes are the instruction manual for building a body. They're little stretches of DNA that tell cells what to do, how tall you'll be, what color your hair is, how your brain gets wired up. Most genes are really old. They go way back, shared with fish, birds, even bacteria. But every now and then, a change pops up, a tiny typo in the genetic code. Most changes don't do much. Some are bad, but sometimes a single change can have a huge effect. FOXP2 is one of those genes. It's not famous like the gene for eye color, but it does something even more important. It helps control how our brains develop for speech and language. How do we know this? Scientists first noticed it in a family in England. The family was called the K family. Most of the members spoke normally, but about half of them struggled with speech, not just a lisp or a stutter. They couldn't form words right. They had trouble with grammar, trouble moving their mouths in the right way. It was like their brains and mouths weren't connecting. Doctors ran test after test. Then, in the 1990s, geneticists found the cause. The affected family members all had a single change in one gene. That gene was FOXP2. This was a big deal. It showed that one tiny spot in our DNA could mess up language. Not just the sound, but the rules, the patterns, the ability to put words together in a sentence. Think about that for a second. There are more than 3 billion letters in the human genome. One letter changed and a person loses the ability to speak and understand language smoothly. So what does FOXP2 do exactly? It acts like a switch. It turns on other genes that help build nerve cells in the brain, especially in places linked to speech, movement, and language. If the switch is broken, speech gets broken, stew. But here's the thing. FOXP2 isn't just found in humans. It's in mice, birds, even fish. Every animal with a backbone has some version of it, but the human version is special. We have 2 changes, just 2 little letters that are different from chimpanzees. That doesn't sound like much. 2 changes out of thousands of letters, but those 2 changes seemed to make all the difference. Scientists mad human for XP2 with the version in chimpanzees. Chimpanzees can make sounds. They can communicate, but they can't speak. They can't use grammar or string together sentences. They can't tell stories. When they put the human version of FOXP2 into mice, those mice started making slightly different squeaks. Their brains wired up a bit differently. It wasn't speech, not really, but it was a clue. In songbirds, FOXP2 is even more interesting. Young birds need this gene to learn their songs. If you block it, they can't learn the right notes. They mess up the patterns. Their brains don't wire up for song. So FOXP2 is old. It's been helping animals learn sounds for a long time. But in humans, it seems to have gotten a power-up, a couple of tiny tweaks, and now we can talk. Here's where timing comes in. When did these changes appear? Did Neanderthals have them? Did earlier humans? Scientists started digging for answers. They looked at ancient DNA from Neanderthals. And guess what? Neanderthals had the same 2 changes in FOXP2 as modern humans. That was unexpected. It meant that the gene didn't appear out of nowhere. It had been around for at least 400,000 years. But then why didn't Neanderthals develop language like us? Maybe they did in their own way. Maybe FOXP2 was necessary, but not enough on its own. Maybe other genes were required too. Maybe culture played a role. Or maybe the way their brains were organized made a difference. Still, FOXP2 stands out. It's a piece of the puzzle. It shows that the machinery for speech was being built long before cave art appeared, long before humans started drawing bison and mammoths on stone walls. Let's break it down a bit more. FOXP2 helps build brain circuits, especially in an area called Broca's area. This spot is on the left side of your brain, just above the temple. It's the control room for speech. If you damage it, you can't form words right. Your grammar falls apart. You know what you want to say, but you can't get the words out. FOXP2 is also active in the basal ganglia. That's a deep part of the brain that helps with movement and habits. Speaking isn't just about thinking. It's about moving the lips, tongue, and throat in a precise dance. One slip and the word comes out wrong. Think about how fast you talk. You string together sounds at lightning speed. Your brain has to plan each movement, every syllable, every pause. FOXP2 helps make that possible. But there's another twist. FOXP2 is also linked to learning. When children learn to talk, they listen, they copy, they practice, over and over. If FOXP2 isn't working right, that learning gets blocked. The child can't pick up the patterns even with practice. So, if you think of language as a symphony, FOXP2 is like the conductor. It makes sure everyone's playing together. If the conductor's missing, the music falls apart. But a conductor can't make music alone. You need instruments, you need musicians, you need a score to follow. FOXP2 wasn't the only gene involved, but it was one of the first to show how a simple change could set the stage for language. Now, scientists have found other genes that play a part. Some help with hearing, some help with memory, some help with the muscles of the mouth and face. But FOXP2 is the star of the show, the first piece that pointed toward a genetic link to language. Let's look at the evidence beyond genes. What about the skull, the bones of the head and throat? Speech isn't just about the brain. It's about the hardware too. Human skulls are different from other apes. The base of the skull is angled in a way that allows for a longer vocal tract. The tongue sits lower. The larynx or voice box is lower in the throat. This lets us make more sounds, more vowels, more consonants, more variety. Their hyoid bone, the little bone in the FOXP2 gene, when language became possible, throat that anchors the tongue, looked almost the same as ours. Some researchers think Neanderthals could speak, at least in some way. But there are differences. The shape of the mouth, the size of the nasal cavity, the way the chin sticks out. These small changes might have made a big difference in the sounds we could make. It's hard to know for sure since soft tissue doesn't fossilize. Then there's the question of culture. Even with the right skull and the right genes, you need a reason to talk. You need other people who will listen. You need something to say. For a long time, early humans might have used simple sounds. Grunts, cries, laughter, maybe a few basic words. But something changed. Language exploded. Suddenly people could string together ideas, ask questions, tell stories, teach each other new skills. FOXP2 didn't create this out of thin air, but it opened the door. It made complex speech possible. Let's go back to the evidence. The K family wasn't the only clue. Scientists have found other families around the world with FOXP2 changes. In every case, the pattern is the same. Trouble with speech and language, trouble learning grammar, trouble putting words together. When you look at brain scans, people with FOXP2 problems show less activity in Broca's area and the basal ganglia. Their brains try to compensate. Other areas light up, but it's not enough. The system can't run smoothly. And here's a strange detail. FXPT2 is also active in the lungs and the heart. No one's sure why. Maybe it's a leftover from our deep evolutionary past. Maybe it helps coordinate breathing with speech. Maybe it's just a side effect. Biology is full of surprises. So, what does all this tell us about the moment humans learn to talk? It looks like language needed a perfect storm. The right genes, the right brain wiring, the right physical changes, the right social setting. FOXP2 was a big part of it, but it wasn't the only player. Other genes have been found that affect language. CNTNAP2, for example, is linked to the way nerves connect in the brain. KA0319 helps with reading and writing. DCDC2 affects how we hear sounds. It's a whole orchestra of genes playing together. But FOXP2 is the one that stands out, the one that showed us language is built into our DNA. What about our closest relatives? Chimpanzees can't talk, even if they're raised with humans. They can learn simple signs. They can understand a few spoken words, but they can't produce speech. Their FAXP2 gene is just a little different, but that tiny difference is enough. Bonobos, gorillas, orangutans, it's the same story. No speech, no grammar, no true language, just gestures and simple sounds. Now, let's talk about the timeline. The two key changes in FOXP2 probably appeared around 500,000 years ago, maybe a bit earlier. That's long before cave art, long before agriculture, long before cities. Neanderthals and Denisovans had those same changes, but something still separated us. Maybe it was how the gene was turned on and off. Maybe it was other genes working together. Maybe it was culture or luck. Here's an experiment scientists tried. They took human stem cells and changed the FOXP2 gene back to the chimpanzee version. Then they grew those cells into tiny brain structures, organoids. The cells with chimpanzee FOXP2 made fewer connections. The brain circuits were simpler. The human version made more connections, more complex wiring. It's not speech, but it's a clue. The change in FOXP2 made our brains connect in new ways, gave us the wiring for language. But genes aren't everything. Think about sign language. But genes aren't everything. Deaf children invent their own signs, even if nobody teaches them. If you put a group of deaf kids together, they'll invent a new language in a few years, with grammar, with rules, with creativity. The brain wants to communicate. FOXP2 just makes it easier. Now, let's look at other animals. Parrots can mimic words. Dolphins use whistles. Elephants rumble in the ground. But none of them build grammar. None of them tell stories about the past. None of them ask why. Some birds have FOXP2 and they need it to learn their songs. But their version is a bit different. It lets them learn notes but not language. So why did humans get the language boost and not other animals? Maybe it's the combination of our big brains and the FOXP2 tweaks. Maybe it's our social lives. Maybe it's our social lives. Maybe it's that feedback loop of helpless babies needing care, which pushed us to cooperate and share information. FOXP2 was one key, but the lock was complicated. Let's talk about what language actually does for us. Why is it so powerful? It lets us share ideas, teach skills, warn about danger, plan for the future, remember the past, lie, joke, comfort each other. Language can be simple, point and grunt, or it can be complex stories, poetry, laws. It can build trust or spread rumors. It can unite a group or start a fight. With language, You don't have to see something to know it's real. Someone can tell you about a herd of animals over the hill, about a storm coming, about a fire in the distance. You can learn from people you never met, from ancestors you never saw. FOXP2 helped unlock all that. It didn't invent helped unlock all speech, but it made it possible. Think about children. By age 3, most kids can speak in sentences. By age 4 or 5, they invent stories. By age 6, they know thousands of words, all without formal lessons. The brain is hungry for language, built to learn it, designed to share it. If the FOXP2 gene is broken, that window closes. Words become hard to learn. Patterns don't make sense. The world gets quieter. Now, something to remember. Language didn't appear overnight. It wasn't a light switch. It was more like a dawn, a slow brightening. At first, maybe just a few words, then short sentences, then stories, then poetry, then laws and myths and songs. FOXP2's changes were a big part of that dawn. Not the whole sunrise, but the first light. There's still a lot we don't know. Maybe Neanderthals told stories around their fires. Maybe Dennis sang lullabies to their children. But the evidence is thin. No written words, no recordings, only bones and tools and a few bits of DNA. What we do know is this: by the time art and symbols start appearing in the record, by the time humans are painting caves and carving statues, the hardware, E for language, was already there. The genes, the brain wiring, the throat, the mouth, all ready to go. The FOXP2 story is a reminder of how small changes can open big doors. 2 tiny tweaks, and suddenly we can share dreams, teach each other, build cultures, change the world. But one gene alone isn't destiny. It's just one piece of a giant puzzle. You need the right environment, the right social group, the right spark. Still, it's amazing to think that every time you speak, every time you tell a story or ask a question, you're using a system built by millions of years of evolution and powered in part by these tiny changes in your DNA. FOXP2 didn't just shape language, it shaped everything that came after. Art, history, science, love, war, all of it built on the foundation of words. And that's why scientists get so excited about this gene. It's not just a code inside your cells. It's a key to understanding what makes us different, what makes us human. So the next time you speak or listen or tell a joke, remember a tiny change made it all possible. And that change is still inside you, working every time you open your mouth. That's the story of FOXP2. Not the whole story of language, but a huge part of it. And as language grew, so did everything else. Stories spread, ideas moved, cultures connected, the world started to change in ways no animal had ever seen before. But language alone wasn't the end of the story. There were more mutations, more changes, more moments that set us apart. Language let us share ideas. But there's another mutation, another twist that made us truly different. So we've talked about language and the gene that helped unlock it. But humans didn't just learn to talk. We learned to imagine, to believe things that aren't right in front of us. That's a much stranger trick, and it's the one that really set us apart. Think about what imagination actually means. It's being able to picture something in your mind that isn't real or isn't real yet. Sometimes it's a memory. Sometimes it's a dream of the future. Sometimes it's something that never happened at all. No other animal on Earth really does this the way we do. Sure, dogs can dream. Apes might plan simple things like using a stick to get ants. But only humans can invent whole worlds. We picture spirits in the wind, monsters in the dark, or heroes fighting battles that never happened. We imagine gods, rules, and stories that shape millions of lives. Here's the big question. Where did this ability come from? Was it just language that made it possible? Or was there something else? Maybe another twist in our DNA that flipped a new switch in our DNA. That flipped a new switch in our brains. Scientists have chased this puzzle for decades. They look for clues in bones, in ancient tools, and in the genes inside our cells. They ask, what made human imagination so powerful? Why us and not chimps or gorillas? Let's start with the basics. Your brain isn't just one lump of thought. It's a web of different parts, all connected. Some parts handle vision, some handle memory, others handle language movement, or emotion. For imagination, you need many of these areas talking to each other at once. There's a special network deep inside your brain called the default mode network. That's the name scientists use, but you can think of it as your daydream engine. It's what lights up when you're not focused on the outside world. You might be staring at the ceiling, thinking about nothing, but inside, your brain is busy. It's replaying memories, building new ideas, and stitching together pictures that don't exist. This network is much more active in humans than in any other animal. In fact, it's one of the things that makes our brains unique. When you imagine, plan, or remember, this part of your brain is hard at work. So what does this have to do with genes? Here's where it gets interesting. The same explosion of culture that brought us cave art, jewelry, and music also lines up with changes in certain genes. Not just FOXP2, but others that help wire up the brain for creativity and imagination. One gene that's come under the spotlight is called HAR1. That stands for Human Accelerated Region. It's a stretch of DNA that changed very quickly after humans split from chimps. Most parts of our DNA change slowly, but H1 picked up more than a dozen changes in a short window of time. What does H1 do? It helps build the brain's cortex, the wrinkly outer layer where thinking happens. In other words, it helps set up the hardware for complex thought. Scientists think changes in H1 made it easier for our brains to grow more connections. More connections mean more ways to link ideas, memories, and feelings. Other genes also play a part. There's SRGAP2, which doubled itself in our ancestors. That extra copy gave our brain cells longer arms to reach out and connect with other cells. More connections, more imagination. Then there's the gene ARCH1B. This one is only found in humans and our closest extinct cousins. It helps the brain grow more progenitor cells during development, which means a bigger, smarter brain. But here's the thing. Having a big brain isn't enough. Elephants and whales have big brains too. What seems to matter is how those brains are wired. The human brain is packed with connections. It's almost like a city lit up at night with lights flickering in every direction. Imagination comes from all those lights talking to each other. Let's take a closer look at what imagination actually does for us. Why did it matter so much in the ancient world? First, it let us solve problems. If you can picture a trap before you build it, you're more likely to catch dinner. If you can dim else's feelings, you're less likely to get in a fight, or you're better at making friends. Imagination lets you test ideas in your mind before risking your life for real. Second, it lets us work together in new ways. Think about a hunting party. Instead of just reacting to what's in front of you, you can plan. I'll hide here. You scare the animals this way. We'll trap them together. That's not just instinct. That's imagination and trust. Third, it lets us believe in things that aren't physically there. This might sound simple, but it changes everything. Money is just a piece of paper, but if everyone believes in it, it works. Laws are just words, but if a whole group agrees to follow them, you get order instead of chaos. Even more basic than that, imagination lets us create stories. Stories are glue that binds groups. They teach lessons. They pass down wisdom. They make people feel connected even when they're strangers. Now you might wonder, did imagination just appear one day? Probably not. It was a slow build, but some scientists think there was a tipping point, a moment when our brains crossed a line. Maybe it was a single gene tweaking the way connections formed. Maybe it was a few changes working together. Suddenly, the lights turned on brighter than ever before. There's one idea called the imagination gene hypothesis. It's not about a single gene, but a group of changes that work together. These changes made it easier for us to imagine, pretend, and believe in things we couldn't see. It's the difference between a child who plays let's pretend and a dog who just chases a ball. Let's break down what makes imagination special. There are a few key parts: memory, prediction, and creativity. Memory is the foundation. You remember what happened before, but imagination takes it further. You remix memories into something new. Maybe you remember a lion chasing you last week. Now you imagine what would happen if 2 lions showed up. Or you picture a safe hiding place you've never actually seen. Prediction is next. If you can imagine what might happen tomorrow, you're better at surviving. You plan for winter. You store food. You avoid places where you once saw danger. Then comes creativity. This is where you invent things that aren't just copies of the past. Maybe you paint a picture of a horse with 7 legs, or you invent a tool no one's ever used before, or you tell a story about a hero who never existed. Children are experts at this. Watch any group of kids playing. They invent whole worlds. They turn sticks into swords, rocks into treasure, clouds into dragons. That's the imagination gene at work. But what about belief? This is the weirdest part of human thinking. We can believe things that aren't real, yet act as if they are. Sometimes that's helpful. You believe in your team, so you try harder. You believe in your team, so you avoid certain actions. Sometimes it's dangerous. People can believe in curses or monsters or enemies that don't exist. Still, belief is powerful. It lets humans form groups around shared ideas. It lets us build religions, nations, and traditions. No other animal does this at our level. Some scientists think this leap in belief came from the same changes that boosted imagination. When the brain is wired to picture things that aren't there, it's easy to start believing in them too. There's evidence for this in the archaeological record. Around 50,000 years ago, we see a burst of strange objects, beads, statues, carved bones. Some of these objects seem magical. Tiny animal figures with no use except to hold or look at. Painted hands on cave walls, footprints left behind for no reason but to say, "I was here." It's not just art for art's sake. These objects show imagination at work. Someone pictured something near and made it real. Let's talk about another experiment. Scientists scanned the brains of people as they imagined things. They found that the same areas light up whether you're seeing something for real or just picturing it in your mind. Another, the cultural explosion. What happened 70,000 years ago? Words. Your brain treats imagination almost like reality. That's why a scary story can make your heart pound even if you know it's fake. That's why you can wake up from a dream sweating even though nothing really happened. That's the power of this new brain wiring. But is this ability unique to modern humans? Or did our extinct cousins have it too? Neanderthals left behind some clues. They made tools that were more advanced than those of earlier humans. They used pigments, maybe for body paint. They haven't buried their dead. But most scientists agree that Neanderthals didn't make the same kind of symbolic art we did. No animal-headed statues, no painted stories on cave walls. Maybe their imagination just didn't reach as far. There's a theory that imagination and belief gave us a survival edge. If you can picture the future, you can avoid danger. If you can tell a story about why the river floods, you can protect your group from disaster. If you believe in a shared symbol like a totem or a flag, you can unite hundreds of people who don't know each other. Imagination also brings risk when you can picture things that aren't real. You can worry about things that might never happen. Anxiety, fear of the unknown, doubts. These are all side effects of our creative brains. But overall, the benefits are huge. Let's get back to the science for a minute. What other genes might be involved in imagination? One is called COMT. It controls how your brain uses dopamine, a chemical that helps with thinking and feeling good. Some people have a version that makes them more creative. Rosé have a version that makes them better at focus and planning. Another gene is DRD4. It's been linked to curiosity and risk-taking. People with certain versions of DRD4 are more likely to explore new places, try new things, and invent new tools. There's also BDNF, which helps your brain grow and change throughout life. High levels of BDNF seem to make people more flexible in their thinking, better at making new connections, and imagining new ideas. But here's the big idea. It's not just one gene. It's a whole network. Genes set up the hardware. Life experience shapes how the wiring gets used. Culture, family, and learning all add layers. It's a bit like having a fancy computer. Genes build the machine. But what you do with it, what programs you run, what games you play, what stories you write, that's up to life. Let's look at some real-world examples of imagination at work. First, cave art. The oldest known cave paintings are over 40,000 years old. Some are in Europe, some in Indonesia. They show animals' hands, even scenes that look like hunting or dancing. Why paint on the walls? No one knows for sure. Maybe it was for magic. maybe to teach others, maybe just for beauty. Either way, these paintings show someone could imagine something, then make it real for others to see. Next, burial rituals. Early humans started burying their dead with objects, beads, tools, even flowers. This suggests they imagined an afterlife or at least cared about remembering. It's not just instinct, it's belief. Stories are another example, oral tales passed down for thousands of years. Myths about the stars, the seasons, the spirits in the forest. Stories that explain where we come from, who we are, and what's possible. Even today, humans are wired for story. We see faces in clouds, patterns in stars, meaning in random events. Our brains crave narrative, that's imagination in action. So why did this leap happen? Some scientists think it was a random mutation, a lucky roll of the genetic dice. Others think it was pressure from the environment. Life got harder, so imagination became a tool for survival. Maybe both are true. Here's where things get wild. Imagination lets us step outside ourselves. We can picture what someone else is thinking or feeling. That's called theory of mind. It's what makes empathy possible. It's why you can feel bad for someone in a story, even if they're made up. Animals show glimmers of this, but humans take it to a whole new level. We can guess what others will do. We can lie, bluff, or act to change their minds. This ability made trade, trust, and teamwork possible. It's the root of every friendship, every alliance, and every betrayal. There's also a downside. Imagination can feed paranoia, jealousy, and fear. But it also makes forgiveness, hope, and love stronger. It's a double-edged sword. Scientists have tried to measure imagination. They use tests where people are asked to invent uses for common objects or to tell stories about pictures. People with brain injuries sometimes lose this ability. Their world becomes flat, full of facts, but no color. Imagination can be fragile. It needs the right wiring, the right chemicals, and the right spark from the world outside. One famous case is the story of feral children, kids raised with almost no human contact. Without people to talk to, play with, or learn from, their imagination stays small. It's like a fire that never gets enough wood. This shows that genes give us the tools, but life gives us the fuel. Let's pause and ask, what does this mean for who we are? Imagination is at the heart of being human. It lets us dream, hope, and build things that never existed. It lets us connect with others, even across time and space. It's the reason we have books, movies, music, and games. But it's also the reason we can worry about tomorrow, or feel sad about things that never happened. It's the reason we can love people we've never met, or miss places we've never been. Our ability to imagine is both a gift and a challenge. And here's something beautiful. Every child, everywhere in the world, is born with the seeds of imagination. Some will paint, some will tell stories, some will invent tools, some will just dream. It's not just artists or writers. Every time you picture a better future, every time you solve a problem, every time you wonder what if, that's imagination at work. So, was there really an imagination gene? Not one single gene. No, but a whole set of changes working together that made our brains more flexible, more creative, more able to believe in things we can't see. This is what let us become more than just another animal. It's what let us become human in a deeper way. And even though we don't know exactly when this leap happened or what triggered it, we can see its fingerprints everywhere, in every cave painting, every song, every myth, every dream. You could say the imagination gene is still working today. Every time you close your eyes and picture something new, the story of imagination isn't finished either. We keep inventing, dreaming, and believing. We build worlds inside our heads, then try to make them real. Sometimes we fail. Sometimes we change everything. And the best part, we're not alone in this journey. For a long time we shared the world with other human species, Neanderthals, Denisovans, maybe others we haven't found yet. The story of imagination is about all of us, every branch of the family tree, every spark of creativity. Some burned out, some burned bright, but that leap, the leap into imagination and belief, changed the world forever. And it all started with a few tiny changes in our DNA and a lot of dreaming. So, we've left about how imagination changed everything for our species. But Here's something even stranger. Humans weren't alone. For most of our history, we shared the world with other kinds of humans, not just one or two, but a whole family tree of cousins, Neanderthals, Denisovans, maybe even more that we haven't found yet. It's wild to think about. If you were alive 50,000 years ago, you might have run into someone who looked almost like you, but not quite. Their faces were a bit different. Their bodies were sometimes stronger, sometimes shorter, but they walked upright, made tools, and in many ways lived a life not so different from yours. Let's try to picture the world back then. Europe wasn't a quiet place. It was cold, full of ice and forests. Neanderthals lived there for hundreds of thousands of years before modern humans showed up. In Asia, Denisovans were holding on in places like Siberia and maybe further south. In Africa, our own ancestors were spreading out, learning new tricks. The evidence is in the bones. Archaeologists have dug up Neanderthal skeletons in Spain, France, Germany, and beyond. Denisovan bones are rare. Just a finger, a few teeth, a piece of skull. But their DNA tells a bigger story. It shows they were a real branch of the human family, not just a footnote. Now, here's where it gets interesting. For a long time, scientists thought we were totally different from these cousins. The story went like this. Neanderthals were slow, simple, and doomed to die out. Denisovan were mysterious and vanished before anyone knew much about them. Modern humans were the heroes, the clever ones who invented everything, and outlasted everyone else, but the evidence doesn't fit that old story anymore. Turns out our cousins were smart in their own ways. Neanderthals made sharp tools called Mutation tools. They used fire, built shelters, even made glue from tree bark to fix stone points onto wooden handles. That's not mindless copying, that's problem solving. Some Neanderthal sites show signs of planning. In Brunel Cave in France, archaeologists found a circle made from broken stalagmites deep underground in total darkness. Someone hauled these heavy stones, stacked them in shapes, and maybe even lit fires around them. The structure is over 175,000 years old. That's 120,000 years before the oldest cave paintings we know about. What does that mean? It means Neanderthals could work together and imagine something that didn't exist before. Maybe it was a shelter, maybe it was for rituals. We don't know, but it's not something you do by accident. And then there's the jewelry. In Spain, scientists found eagle talons with cut marks on them, like someone was turning them into necklaces or ornaments. Some shells have traces of pigments, maybe used as paint. These finds are over 40,000 years old, before modern humans reached that part of Europe. Some people think this is proof that Neanderthals had art, or at least cared about beauty. Others say it's not quite the same as the paintings and statues made by modern humans. But one thing is clear, they were doing more than just surviving. Let's talk about burial. There are Neanderthal graves with bodies placed carefully in the ground, sometimes with flowers or tools. Did they believe in an afterlife, or was it just respect for the dead? We can't ask them, but it shows they thought about death in a way that goes beyond instinct. Now, what about Denisovans? The truth is, we know less about them. They left almost no art or tools behind that we can be sure of, but their DNA is everywhere. If you have ancestors from Asia or Oceania, you probably have a little Denisovan DNA in your blood. That means our species met, talked, and sometimes had children together. That's not just a theory. Scientists can read it in our genes. If you look at people from Papua New Guinea, up to 5% of their DNA comes from Denisovan. In East Asians, it's less, about 0.2%. Even people from Europe and the Americas have small amounts. Neanderthal DNA is even more common. Almost everyone outside Africa has about 1%, 2% Neanderthal DNA. Some people have more, some a little less. These aren't just numbers. They're living proof that our ancestors and our cousins met and mixed and left a mark on each other. Here's a weird detail. When scientists looked at the Neanderthal genome, they found some chunks of DNA that are almost never seen in modern humans. These pieces are missing because they made people less healthy or less able to have children over time. Those genes faded out, but some Neanderthal genes stuck around. They helped fight off diseases or survive in cold weather. For example, there's a gene that controls how your skin reacts to sunlight. People with Neanderthal versions of this gene can handle less sunlight without getting burned. That's handy if you live in cloudy, northern places. Another gene from Neanderthals helps your body fight off viruses, especially ones that attack the immune system. During the COVID-19 pandemic, scientists found that having a certain Neanderthal gene could make the disease worse, but another Neanderthal gene seemed to protect against it. It's a reminder that these ancient encounters still shape our lives today. But let's get back to the big question. How did these different humans interact? What was it like when two branches of the human family met, in a forest, or by a river, or in a cave? The evidence says it happened more than once. In Europe, modern humans and Neanderthals shared the land for thousands of years. There are layers in caves where you see Neanderthal tools, then modern human tools, then Neanderthal ones again. Sometimes, both kinds of tools are found in the same layer, as if the groups were living side by side. Some scientists even think they traded ideas. For example, after modern humans arrived in Europe, Neanderthal tools got more complex. They started making smaller blades and even using bone and antler for points. Maybe they copied what they saw, or maybe the two groups worked together for a while. But it wasn't all sharing and peace. There's also evidence of violence. Some Neanderthal skulls show signs of injuries, maybe from fighting, but that's not proof of war. It could be from hunting accidents, or even accidents in daily life. Still, it's likely there was tension, maybe even competition, for food and shelter. One thing is certain, these meetings changed both groups. Neanderthals started to disappear about 40,000 years ago. By 30,000 years ago, they were gone. Denisovans lasted longer in some places, but they too vanished. Why did our cousins die out while we survived? That's one of the biggest mysteries in science. Some say it was climate change, a series of cold snaps that made life impossible in Europe and Asia. Others say it was disease brought by modern humans from Africa. Still, others think it was competition for resources, or even just bad luck. But maybe the answer is more complicated. Maybe it wasn't just one thing. Maybe it was a mix of tough weather, shifting food sources, and new people arriving with different skills. There's another piece of evidence. Tools and art from the time when Neanderthals and modern humans lived together. In France, at a cave called Châteauron, archaeologists found layers of tools that mix styles from both groups. Some bone points look like classic modern human tools, but they're found with Neanderthal remains. Were Neanderthals copying what they saw, or was there real exchange with people teaching each other how to make new things? No one can say for sure, but it looks like the boundary between us and them wasn't always clear. Let's not forget Denisov. In a cave in Siberia called Denisova Cave, scientists made an amazing discovery. They found the bone of a girl who had a Neanderthal mother and a Denisovan father. That's right. She was a first-generation hybrid. It's not just mixing over thousands of years, but real families with parents from two branches of the human family tree. Other fossils from the same cave show Denisovans and Neanderthals lived there, maybe at the same time, maybe in turns. The cave was used for over 250,000 years. That's longer than the entire history of modern civilization. Genetics tells us even more. Some genes from Denisovan help people today survive at high altitudes. For example, Tibetans have a special version of a gene called EPA1. It lets them live and work where the air is thin, like on the Tibetan plateau. This gene came from Denisovan, not from modern humans. Without it, life above 14,000 feet would be much harder. So, the mixing of humans wasn't just random, it gave us real advantages. It let our species adapt to new places. New. Was it mutation or gradual development? Diseases, new climates. But at the same time, something about us was different. Even with all this mixing, something about our brains, our culture, or our imagination gave us the edge. We made art that lasted. We built bigger networks. We told stories that pulled people together. Let's zoom out and see just how many kinds of humans there were. At least 4 or 5 branches lived at the same time. In Indonesia, there was Homo floresensis, sometimes called the Hobbit, because they were less than 4 feet tall. In the Philippines, scientists found Homo lucenensis, another small human with weird teeth and bones. In southern Africa, There's evidence for a group called homonali. Each group had its own way of living. Some made simple tools, others made complex ones. Some stayed in small groups, others may have formed bigger bands. Now, picture the world as a patchwork. Different types of humans, each with their own customs and ideas. Sometimes meeting, sometimes avoiding each other, sometimes mixing. It wasn't a straight line from ape to modern human. It was more like a tangled bush with branches crossing and twisting together. Here's a cool detail. In Israel, archaeologists found caves where Neanderthals and modern humans both lived. Sometimes their bones are only a few feet apart, but they're separated by thousands of years. It's as if the land itself remembers the meetings and the goodbyes. What about language? Did Neanderthals talk like us? That's a tough one. Their skulls show they had the right shape for speech, bones for hearing, jaws for making sounds. The FOXP2 gene, the one link to language, was almost the same in Neanderthals as in us. Maybe they spoke, but their language was simpler or less creative. Or maybe it was just different. No one has found Neanderthal writing or clear symbols like the ones modern humans left behind. But absence of evidence isn't proof they didn't have language. Maybe their words were never written down. Maybe their stories were lost in time. Let's look at the evidence for group size. Modern humans seem to live in bigger groups than Neanderthals. Archaeologists think Neanderthal groups were usually small, maybe 10 to 20 people, sometimes 30. Modern humans, though, formed bands of 50 or more. Bigger groups mean more ideas, more sharing, more chances for creativity. That could be a big reason why we survived and others didn't. It's easier to weather tough times with a big group. You can share food, care for children, and pass on knowledge. If one person has a new idea, it spreads faster. Now, what about culture? Modern humans seem to have or layers, more art, more trade, more long-distance travel. In Africa, beads made from ostrich eggshells are found hundreds of miles from where they were made. That means people were trading or at least traveling far from home. Neanderthals mostly used local materials. Their tools rarely traveled more than a few dozen miles. That doesn't mean they were stuck. It just means their networks were smaller. But there are exceptions. In France, Neanderthals used volcanic rock that came from over 100 miles away. Maybe they traded with other groups, or maybe they traveled long distances themselves. There's still so much we don't know. Let's talk about children. The way a group treats its children can tell you a lot about its culture. Modern humans made tiny beads and ornaments, some small enough for a child to wear. In some graves, children are buried with care, sometimes with toys, sometimes with special objects. A famous grave in Russia called Sunhai has 2 children, buried side by side, covered in beads, ivory pins, and even spears. The beads took thousands of hours to make. That's a sign of love, or at least of special meaning. Neanderthal child burials are rare, but they exist. In Spain, a Neanderthal child was buried with a stone tool and some bones. Maybe it was a token, or maybe just something to keep the body company. We can only guess. All this evidence paints a picture that's much messier than the old story of us versus them. For a long time, the idea was that modern humans wiped out the others, but now it looks more like a slow blending, a fading away, and a few moments of real connection. The world we live in is shaped by all those meetings, every handshake, every argument, every child born from 2 different groups. Those moments changed us. Here's what's really wild. If you could line up every human who ever lived, you'd see more diversity in the past than we see today. Different faces, different bodies, different ways of thinking, but underneath the same spark, a drive to survive, to create, to belong. So what does all this mean? It means we're the product of many experiments. Some branches ended, some merged, some got lucky. But everyone added something to the story. When you look at your hands, your face, your memories, you're carrying pieces of all those other humans, not just DNA, but echoes of their lives. The way you handle cold, the way you fight disease, even the way you dream might be shaped by someone who lived and died before your ancestors ever left Africa. And think about this. There are genes in your body that came from people we only discovered a few years ago. Denisovin weren't even known until 2010, but their DNA lives on. Who knows what other surprises are waiting in our genes? Some scientists believe there were even more lost relatives. Humans we haven't found yet. Every year, new bones turn up in caves, or teeth in riverbeds, or DNA in the dirt. The story isn't finished. Now you might wonder, does any of this history change who we are today? In some ways, yes. Some people have genes that help them handle fat-rich diets thanks to Neanderthals. Others have genes that shape their immune systems or the way their bodies react to stress. But in other ways, we're all the same. We're storytellers, dreamers, builders, and wanderers. We're shaped by a past that's messier and more interesting than we ever guessed. Here's one last detail. When scientists look at ancient DNA, they sometimes find pieces that don't match any known human group. They call this ghost DNA. It's from cousins we haven't met yet, lost branches of the family tree waiting to be discovered. So, the next time you wonder where you come from, remember you're not just the child of one species, but of many. You're the product of chance meetings, long-joured nays, and strange twists of fate. And even though we're the only humans left, we carry the legacy of all the others. Their struggles, their dreams, their secrets, all mixed together in the people alive today. Some of those ancient genes are still working even now. They help us handle new challenges, new places, and new diseases. They shape the way we look, the way we act, and maybe even the way we think. Our story isn't just about one lucky mutation. It's about a world full of humans crossing paths, sharing ideas, and sometimes falling in love. It's about survival, yes, but also about connection, and that's the real magic of our past. We didn't just outlast our cousins. We became something new, something stronger, by carrying a little bit of all of them with us. Some of those ancient gifts, those borrowed genes still show up in surprising ways, and the story of how they affect us today is just as fascinating. Let's take a closer look at what all this mixing left behind. When people talk about our DNA, it sounds like a code only scientists can read, but it's not magic, it's just a record, a logbook of every twist and turn our ancestors took. And some of the strangest entries in that book come from the genes we inherited from other kinds of humans. Think about your family. Maybe you have your mom's eyes or your dad's laugh. It's the same with our ancient family tree. But instead of just hair color or height, some of these old genes do much stranger things. Here's the first thing to know. Not all genes from Neanderthals or Denisovans were helpful. In fact, many were harmful or just didn't fit with our bodies. Over thousands of years, natural selection, a kind of slow, invisible sorting process, pushed a lot of those genes out. People who had combinations that didn't work well were less likely to survive or have kids. So those versions faded, but some genes stuck around. Why? Because in certain situations, they gave people a better chance. Maybe they helped fight off a disease, or they made it easier to handle the cold, or they helped bodies work better at high altitudes. Let's break this down with some real examples. Start with the immune system, the body's defense against germs. A lot of the genes we kept from Neanderthals and Denisovans have to do with fighting sickness. Scientists found that some modern people have versions of a gene called TLR6, TLR1, and TLR10. These are part of the immune system's early warning systems. The Neanderthal versions of these genes help the body spot bacteria and viruses faster. That can mean you get sick less often or recover more quickly. But there's a flip side. Sometimes a gene that helps in one way causes problems somewhere else. For example, some of these Neanderthal immune genes are linked to allergies. They make the immune system a little too jumpy. That was great when people were surrounded by dangerous germs, but now it can mean more people get hay fever or asthma. So the genes that protected your ancestors might be giving you a runny nose today. That's evolution for you. Never perfect, always a trade-off. Now let's talk about skin and sunlight. When modern humans moved into Europe and Asia, they found less sun than in Africa. Neanderthals had been living in these places for a long time. Some of their genes helped deal with low sunlight. One example is a gene that affects how much vitamin D your skin makes. People with Neanderthal versions of this gene are better at making vitamin D when there's not much sun. That could be a big deal if you live in a cloudy northern place. If your body can't make enough vitamin D, you get weak bones. And children can get a disease called rickets. But again, it's not always simple. Some of these skin genes also change how your skin reacts to sunlight, so may make you more likely to burn. Others help you tan. It's a balancing act. Too little sun is a problem, but too much can be too. Here's something a lot of people don't know. Even our hair and the shape of our bodies can be influenced by ancient genes. There's a gene called BNC2, which affects skin color and freckles. Some versions came from Neanderthals, and they're still found in Europeans today. That's why some people freckle in the sun instead of just tanning or burning. Let's switch gears and talk about Denisov genes. Remember that gene called EP1. It's the one that helps Tibetans live high up in the mountains. If you visit Tibet, you're way above sea level. The air is thin, it's hard to breathe, and most people from other places get sick if they stay too long. But people whose ancestors lived there for a long time have a version of EPA as one that lets their bodies use oxygen more efficiently. Scientists looked closely at this gene. They found it doesn't match what you see in African or European people. Instead, it looks almost exactly like the version from Denis, who lived in Asia long before modern humans showed up. That's not a small thing. Without that gene, life on the Tibetan plateau would be miserable. With it, you can climb mountains, herd animals, and even run marathons at high altitude. Here's another detail. Some Denisvan genes are found in people from Papua New Guinea and nearby islands. These genes seem to help with fighting local diseases and handling heat or humidity. Imagine trying to live in a rainforest if your body can't handle the bugs or the heat. These ancient genes might be the reason some groups thrived while others didn't. Let's pause and think about what this means. We usually talk about evolution like it's a straight line, one change after another, always moving forward. But in our case, it's more like a patchwork quilt. Every time two groups of humans met and had children, new combinations were possible. Some stuck around because they worked. Others vanished because they didn't. Now you might be wondering, how do scientists know all this? How can they point to a gene and say that came from Nurnsay, that came from Munsavens? It's a good question. The answer is DNA sequencing. Scientists compare the DNA in ancient bones to the DNA in people living today. When they find a section that matches ancient DNA, but not the usual modern patterns, they know it came from those older humans. For example, scientists found that about 2% of the DNA in people from Europe and Asia comes from Neanderthals. In some Asian and Pacific groups, up to 5% is from Denisovans. These aren't just random bits. They're specific stretches that show up over and over. Sometimes the ancient versions are only found in people from certain places. That's a clue that those genes helped people survive local challenges. Maybe it was a new disease, a different climate, or strange new foods. Let's get even more specific. There's a gene called HYAL2. It helps protect skin from UV rays, like a built-in sunscreen. Some Asian people have a version of this gene from Denisvan. It helps handle strong sunlight, which can be a big deal in places close to the equator or on high mountains. Another gene called SLT16, A11, is more common in people from Central and South America. Scientists think it came from Neanderthals, or maybe another lost cousin. The strange part, it's linked to a higher risk of type 2 diabetes today. Number one is sure why. Maybe in the past the gene helped store fat when food was hard to find. Now that food is everywhere is not so helpful. That's a theme you'll see again and again. Genes that helped in the past can cause problems now. Our bodies evolved for a world of scarcity, danger, and constant change. Modern life is different. Some mutations that were once useful now make us sick or just don't fit our lifestyles. Let's talk about sleep for a minute. Not the kind you're drifting into now, but how our bodies keep track of time. There are genes that control our body clock, the rhythms that tell us when to wake up and when to sleep. Some of these clock genes have Neanderthal origins. Scientists found that people with these versions are more likely to be early risers. Maybe that helped ancient people get up with the sun or work longer in the short days of winter. But it's not always good news. Some Neanderthal clock genes are also linked to depression or trouble sleeping in modern life. It's a reminder that every gene is shaped by the world it came from. Change the world, and the same gene can turn from friend to foe. Here's another area where ancient genes still show up: our sense of smell. One study found that certain Neanderthal genes change how people smell and taste things. Some people are super sensitive to certain odor. Others barely notice them. In the past, this might have helped spot dangerous foods or sniff out prey. Today, it might just make you picky about what you eat. Let's get into something most people never think about: blood. There are different blood types, a BABO, and each has its own story. But there are also rare blood groups that come from our ancient cousins. For instance, some people in Asia and Australia have a blood type that matches what scientists found in Denisovan DNA. It's rare in the rest of the world, but common in places where Denisovans once lived. These rare blood types can cause trouble with transfusions, but they also show how deep the mixing goes. Even something as basic as blood carries the mark of conscient meetings. Now think about the skeleton. Some people have bones that are a little thicker or stronger. That's not just from exercise, or diet. Certain Neanderthal genes are linked to denser bones and wider rib cages. In the past, this might have helped with heavy work or just staying warm in the cold. Today, it might mean you're less likely to break a bone, or maybe you just have a stockier build than your friends. But not every old gene is a benefit. Some Neanderthal genes are linked to a higher risk of addiction or even mood problems. For example, one gene is connected to nicotine addiction. Another, called IS1, affects how your body fights viruses, but can also make you more likely to get sick from certain illnesses, like COVID-19. It's a mixed bag. Some genes help, some hurt. Most just sit there silent until something in your life brings them out. Let's talk about teeth. Denisovan DNA is linked to large murs, big strong back teeth. These are useful if you're eating tough plants or raw meat. But in the modern world, big teeth can mean crowded mouths or dental problems. Still, if you, other genetic accidents that made us human, look at people in some Asian or Pacific groups, you can sometimes see these traits. Here's another detail. Some people have a gene that gives them a little bump on the back of their skull, called an occipital bun. Neanderthals had these too. No one's sure what it did. Maybe it helped with heavy muscles in the neck, or just made the head stronger. Now you might ask, are these differences really that big? For most people, the answer is no. The differences are small, just 1% or 2% of your DNA, or a tiny change in how your body works. But in the past, these little differences could make the difference between life and death. Imagine you're living in Ice Age Europe. It's freezing, food is scarce, and danger is everywhere. Having a gene that helps your body burn fat or keep your skin tough might mean you survive, while others don't. Or picture life in the tropics. Mosquitoes carry deadly diseases. A gene that makes your immune system a little better could be the difference between living and dying before the age of 5. That's why natural selection is so powerful. It doesn't care about fairness. It just keeps what works and tosses what doesn't. Let's look at another example. Pain. Some people are more sensitive to pain than others. Scientists found a gene inherited from Denisovans that makes people in Southeast Asia and Oceania feel pain differently. Sometimes it means they feel pain more strongly, sometimes less. In the past, this could have helped people avoid danger or push them to heal faster. Today, it just means some people have to be more careful with medicine. Here's a fun fact. The fat under your skin, what's called subcutaneous fat, can be influenced by Neanderthal genes. People with certain versions are better at storing fat, which helps in cold weather or when food is scarce. In the modern world, it might just mean you struggle with weight or stay warmer in winter. Let's talk about height. Some ancient genes are linked to being slightly shorter or stockier. Neanderthals were famously robust, thick bones, wide bodies. Some of those traits persist, especially in European populations. But again, it's just a piece of the puzzle. Your height comes from hundreds of genes, not just 1 or 2. Now, what about disease? Some Neanderthal genes help protect against diseases like the flu or hepatitis. Others make people more likely to get certain autoimmune diseases where the body attacks itself. It's the same story again. A gene that helped in one time or place can cause problems in another. Let's talk about hair. Neanderthal genes can affect hair thickness and shape. Some versions are linked to straight hair, others to slightly wavy hair. It sounds like a small thing, but in cold places, thick hair can be a real advantage. Here's something you might not expect. Some ancient genes help control how your body handles fat and sugar. In the past, these genes helped store energy when food was scarce. Today, with food everywhere, they can make people more likely to get diabetes or heart disease. Let's step back for a second. Why do we still have these ancient genes at all? Why didn't natural selection get rid of all the ones that cause problems now? The answer is timing. Natural selection works slowly. A gene that helped people survive 20,000 years ago might only start causing trouble in the modern world. If that gene mostly affects people after they've had children, it's less likely to get weeded out. Plus, genes don't act alone. They interact with each other and with the environment. What's helpful in one place might be harmful somewhere else. Think about lactose tolerance. The ability to drink milk as an adult. That gene spread in Europe and parts of Africa because people started harrying animals and drinking milk. It's a great example of how culture and genes work together, but it's not from Neanderthals or Denis. It's a new mutation. Still, it shows how quickly genes can spread if they're useful. There are other examples too. The sickle cell gene protects against malaria, but can cause sickle cell disease if you get 2 copies. It's a trade-off. Nature is full of them. Let's not forget the ghost DNA scientists found. Those strange pieces that don't match any known group. These might come from lost cousins we haven't found yet. They could be the next big discovery. Who knows what new traits or diseases they might explain. All of this tells us something important. Our bodies are like museums, holding on to little souvenirs from every stop along the way. Some are helpful, some are just weird, some are problems waiting to happen, but all of them are part of our story. It's easy to think of evolution as a steady climb, always getting better. But the truth is messier. It's a jumble of old and new, of borrowed tricks and lucky breaks. The genes we inherited from Neanderthals and Denisovans and maybe other humans we haven't even named are more than just curiosities. They're proof that survival isn't about being perfect. It's about being good enough long enough to pass your genes on, and sometimes being good enough means borrowing from your neighbors, even if those neighbors are another kind of human. So next time you look in the mirror, remember every freckle, every all-age, every odd reaction to sun or sleep or food might be a tiny echo of a meeting that happened tens of thousands of years ago. Somewhere in a cave or a forest or on a chilly mountain slope, 2 humans met and the world changed, just a little. That's the real legacy of our inherited mutations. Not just survival, but adaptation. Not just blending, but transformation. We're a living record of every experiment nature ever tried on the human body. And the story keeps unfolding even now. So what about the changes that are still happening? What proof do we have that evolution didn't stop with the Neanderthals or Denisovans or even with our early ancestors who look just like us? Let's get into the evidence for recent evolution, the kind that's still shaping people alive today. First, let's get one thing straight. Evolution doesn't have an off switch. It's not something that only happened in caves and ancient forests. It's happening now. It's not always obvious because it works slowly, but if you look closely, you can see its fingerprints all over the place. Start with something simple: milk. Most mammals can drink milk only as babies. After they're weaned, they lose the ability to digest it. Their bodies stopped making the enzyme called lactase, which breaks down milk sugar. But in some humans, this changed. People in parts of Europe, East Africa, and the Middle East can drink milk as adults. That's because of a mutation, a small tweak in DNA that lets them keep making lactase their whole lives. This isn't ancient history. Scientists think the first people with this mutation lived about 7,500 years ago. That's not long at all if you think about how old humans are. Before farming, no one really drank animal milk. But when humans started herring cows, sheep and goats' milk became a new source of food. People who could digest it had an advantage: extra calories, more protein, and a clean drink when water was dirty. Archaeologists found bones with marks of dairying, and DNA tests show the spread of the lactase mutation. In just a few thousand years, The gene went from rare to common in some places. Today, about 90% of Northern Europeans can drink milk as adults. In East Asian and Native American groups, it's less than 10%. That's evolution in fast forward. Now let's look at something deadly: malaria. This disease has shaped the human body in a big way, especially in Africa, India, and parts of the Middle East. Malaria comes from mosquitoes. It kills hundreds of thousands every year, mostly children. Some people have a gene that changes the shape of their red blood cells. If you have one copy, you're less likely to get really sick from malaria. But if you have 2 copies, you get sickle cell disease, a serious illness. The sickle cell gene is a classic example of a trade-off. In places with lots of malaria, the gene sticks around. It's worth the risk because more children survive. In places without malaria, the gene fades away. Scientists proved this by studying blood samples from all over the world. The sickle cell gene is common in areas with malaria and rare everywhere else. That's not an accident. It's evolution, plain and simple. There are other genes that fight malaria too. For example, some people in Southeast Asia have a gene that makes their red blood cells less attractive to the parasite. Others have a gene called G6PD deficiency. It can cause problems with certain foods or medicines, but it helps protect against malaria. All these changes happened in the last few thousand years. They're still happening now. What about diseases that came after farming started? When people began living in big groups, new problems showed up. Tuberculosis, measles, and smallpox are all diseases that spread easily in crowds. Over time, people in some places develop genetic defenses. One example is the CCR5 gene. Most people have a version called CCR5 delta 32. This mutation makes it harder for HIV to enter cells. Scientists think it may also have protected people from smallpox or the plague. The mutation is most common in Europe, where these diseases hit hardest. It's rare in Africa and Asia. The gene probably spread in the last 1,000 years after huge outbreaks. Now let's talk about skin color. Humans started out in Africa with dark skin that protected against strong sun. When groups moved north into Europe and Asia, the sun was weaker. Light skin helps people make more vitamin D from sunlight. Over thousands of years, genes for lighter skin became more common in these places. But it didn't happen just once. Scientists found that different groups got lighter skin in different ways. Europeans, East Asians, and some groups in India all have light skin, but the genes are not always the same. It's like nature tried out several solutions to the same problem. There's a gene called SLC24A5. Almost everyone in Europe has the light skin version. In East Asia, a different gene called OC2 plays a bigger role. These changes happened in the last 20,000 to 30,000 years. That's after people had already left Africa and settled in new places. Here's something that might surprise you: blue eyes. The gene for blue eyes didn't exist 10,000 years ago. Ancient skeletons from Europe show that almost everyone had brown eyes. Then a mutation popped up, probably around the Black Sea. It spread quickly. Today, millions of people have blue or green eyes because of this one change. But why did blue eyes spread? No one knows for sure. Some scientists think it's just random. Others say maybe it helped people see better in low light. Or maybe people just liked the look and chose partners with blue eyes. That's called sexual selection, when a trait spreads because people find it attractive. Now let's talk about high places. People live in the Andes, the Himalayas, and the Ethiopian highlands. Places where the air is thin, your body needs oxygen to survive. At high altitude, there's less oxygen, and it's easy to get sick or even die. People in these places have special genes that help, and then Tibetans have a gene called EPA1. It lets them use oxygen more efficiently. We talked about this in relation to Denisovin, but here's the thing: it's not just ancient mixing. There's evidence that the gene kept spreading and changing even after the original mixing event. The version in Tibetans is even more finely tuned for their environment. In the Andes, people don't have the same gene. Instead, their bodies make more red blood cells. Ethiopians have yet another solution: different genes that help their blood carry oxygen. 3 different groups, 3 different answers. It's proof that evolution keeps working even when the problem stays the same. Let's look at another example, diet. When people started farming, their food changed. In places where rice is the main crop, like East Asia, people have a gene, and that helps them handle starch. The gene is called AMU1. It tells your body how many copies of the enzyme amase to make. More copies mean you break down starch better. Scientists found that people from farming cultures have more copies of this gene than people from hunting and gathering groups. It's a small thing, but it adds up. If your body can turn rice or wheat into sugar faster, you get more energy from the same bowl of food. Here's another twist. Some people can taste bitter chemicals better than others. The gene is called TAS238. About 25% of people can't taste certain bitter flavors at all. The rest find them very strong. This matters because some plants are poisonous and taste bitter. In some places, being able to taste bitter, in some places, being able to taste bitterness might have saved lives. In others, it might just mean you're picky about vegetables. Let's talk about disease resistance again, but from a different angle. Europeans and Asians have genes that help them fight off diseases that came from animals like the flu or measles. These diseases didn't exist before people started farming and living with animals. The genes that help fight them spread in the last 10,000 years. In places where farming started, later, these genes are less common. This is one reason why diseases brought by Europeans were so deadly in the Americas and Australia. The local people didn't have the same genetic defenses. Evolution hadn't had time to work. Here's a wild example. Wisdom teeth. Most people have to deal with them at some point. But some groups like the Inuit and certain East Asian populations often don't grow wisdom teeth at all. Scientists think this is a recent evolution. These groups switched to eating softer food like fish or cooked grains. Over time, people with smaller jaws and fewer teeth had fewer problems. The gene for missing wisdom teeth spread. Now, it's common in some places, rare in others. What about height? In the Netherlands, people are on average the tallest in the world. Scientists found that genes for height have become more common there in the last 150 years. It's not just diet or better healthcare. Tall people in the Netherlands tend to have more children. Their genes are spreading fast. This is evolution you can measure in real time. Now let's look at something you can't see, how your body handles fat and sugar. In some Pacific islands, people have a gene called CREB. RF. It makes their bodies store fat easily. This was probably helpful in the past when food was hard to find. Now it means people are more likely to gain weight and have diabetes. The gene is very common in places like Samoa, but rare elsewhere. This is another example of evolution creating a trade-off. What helped in one time or place can be a problem today. Let's talk about smell. Some people can smell certain chemicals like the ones in asparagus or fish much better than others. This comes down to genes like O2M7. In the past, being able to smell spoiled food or danger was useful. Now it just means some people avoid certain foods or notice smells, others don't. Here's a story about alcohol. In East Asia, many people have a gene called Al2-derms. It makes it hard for their bodies to break down alcohol. People with this gene flush red and feel sick when they drink. Scientists think this gene spread because it protected people from drinking too much, which could lead to accidents or fights. Or maybe it helped protect against a disease called esophageal cancer. The real reason is still debated, but the change is real. Now let's look at the immune system again, but with a new detail. Some people carry a gene called HLA-B27. It helps fight certain infections, but also raises the risk for diseases like arthritis. This gene is common in some groups and rare in others. It shows that evolution doesn't always fix problems. It just balances risks. What about hair? In East, why accidents matter. Evolution isn't about perfection. Asia, there's a gene called EDAR. It makes hair thicker and straighter. It also changes sweat glands and teeth shape. This gene became common about 35,000 years ago. Scientists think it helped people stay warm in cold climates. Or maybe it protected babies from losing too much heat. It's a small change, but it spread fast. Now, let's talk about how people handle sunlight. In parts of Africa, a gene called SLC24A5 keeps skin dark and protects against burning. In Scandinavia, another gene promotes light skin, helping people get more vitamin D. In Australia, Aboriginal people have unique genes that protect against strong sunlight, but not in the same way as Africans. This is evolution, working on the same problem, but finding different answers in every place. There's also evidence of recent evolution in how people react to altitude sickness. In Peru, people living above 10,000 feet have bigger chests and lungs. Their bodies can take in more air with each breath. This is not just getting used to it, it's genetic. Children born to parents who lived in the lands don't have the same advantage. Let's talk about disease again. This time, COVID-19. Scientists found that some people have gene variants that make them more likely to get very sick from the virus. Some of these genes are new mutations that spread in the last few thousand years. Others are older but became more common as people started living in cities. Now, what about brains? Are our minds still evolving? That's a hard question. Some scientists think that genes for brain size and shape are still changing. For example, there's a gene called ASPM. Changes in ASPM can affect brain growth. Some versions spread quickly in the last 6,000 years. No one knows exactly why. Maybe it helped people learn new skills. Or maybe it's just random chance. There are also genes linked to language. One famous gene is FOXP2. It helps control the muscles used for speaking. All humans have it, but some small changes appeared. In the last 200,000 years, these changes are not found in Neanderthals. This suggests our ability to speak and understand language is still a moving target. And then there's the question of mental health. Some genes linked to depression, anxiety, or even schizophrenia have become more common in recent times. It might seem strange, but maybe these traits helped in the past. For example, people who are more anxious may have been better at spotting danger. Now, in a world with fewer threats, those same genes can cause trouble. Let's talk about adaptation to cold. In the Arctic, people like the Inuit have genes that help them process fat from fish and sea mammals. These genes help keep their bodies warm and give them energy. In contrast, people from the tropics have genes that help them sweat more and cool down. Here's a detail. Abo, Ute salt. Some people are salt sensitive. Their blood pressure goes up when they eat salty food. This trait is more common in people whose ancestors lived in hot places where sweating caused them to lose salt quickly. Keeping salt in the body was a survival trick. Now with salty diets and less sweeting, it can be a problem. Let's talk about teeth again. In some African groups, a gap between the front teeth is common. Scientists found a gene called AXIN2 that is linked to this trait. It doesn't cause any health problems, but it shows how even tiny details can be shaped by recent evolution. Now, let's look at how people deal with cold water. In Japan, a group called the AMO have been diving for shellfish. For more than 2,000 years, scientists found they have a higher percentage of body fat, and their bodies respond to cold by narrowing blood vessels in the skin. This helps keep their core warm. It's likely a result of both practice and small genetic changes. What about hearing? In some African groups, there are genes that make hearing more sensitive at certain frequencies. This might have helped with hunting or communication in dense forests. Let's talk about fingerprints. No two people have the same pattern, but some groups tend to have more whorls or loops. Scientists don't know why, but they think it might be linked to genes that help with gripping objects or sweating. Now, how about the ability to digest alcohol? In Europe, most people can handle alcohol without flushing. In East Asia, many can't. This difference comes from a mutation that appeared about 7,000 years ago. It spread in some places but not others. It's another example of how recent changes can stick around if they help, or just linger if they don't hurt too much. Let's talk about vision. In the Arctic, people have genes that help protect their eyes from too much glare off snow and ice. In the tropics, Genan S help people see better in low light. These are small tweaks, but they matter in daily life. Now, let's look at how people react to different foods. Some people can eat spicy food without any trouble. Others can't handle even a little heat. This comes down to genes that control pain and taste receptors. In places like India and Mexico, people have more of the spicy-tolerant versions. This might have helped them enjoy food with more chili, which also kills bacteria and makes food safer to eat. Here's another twist: height and body shape. In hot places, people tend to be taller and slimmer. In cold places, people are shorter and stockier. This isn't just about food, it's about how bodies lose or keep heat. Scientists found genes that help shape these differences. Over time, the people whose bodies fit their environment survived and had more children. What about the ability to handle stress? In some parts of the world, people have genes that help them stay calm under pressure. In other places, different genes make people more reactive. These traits might have helped in different ways, either by staying cool in a crisis or by acting quickly when something went wrong. Let's talk about sleep again, but this time about naps. In some cultures, people take regular naps during the day. Scientists found genes that make people more likely to be natural nappers. In Spain, Greece, and parts of Latin America, these genes are more common. It might sound tiny, but in hot climates, sleeping through the hottest part of the day makes sense. Now, what about response to high-carb diets? In Asia, where rice has been eaten for thousands of years, people have genes that help them process carbs more efficiently. In Europe, where wheat and dairy were staples, other genes became more common. This shows how the food you eat can shape your DNA over time. Let's look at something you might not expect: earwax. There are two types, wet and dry. People from East Asia mostly have dry earwax. People from Africa and Europe have wet earwax. The gene responsible is called ABCC11. It also affects how much people sweat. Scientists think this change is only a few thousand years old. Here's a quirky one: how people handle caffeine. Some people can drink coffee at night and still fall asleep. Others stay awake for hours. This comes down to a gene called CYP1A2. The fast version lets you break down caffeine quickly. The slow version means you feel the effects longer. In places where tea and coffee have been drunk for centuries, the fast version is more common. Let's talk about the gut. Some people have genes that help them digest seaweed, like nori in Japanese food. These genes came from bacteria in traditional diets. Over time, they got passed into human DNA. This is called horizontal gene transfer, a rare but amazing thing. It shows that evolution can sometimes take shortcuts. Now, how do people deal with pain? In some Middle Eastern and South Asian groups, there are genes that make people less sensitive to certain kinds of pain. This might have helped with survival in harsh environments, or just been a random change that stuck around. What about the sense of direction? Some groups, like the Inuit, are famous for their navigation. Scientists are starting to find genes that might help with spatial awareness. It's still early days, but the evidence is growing. Let's look at the immune system. One more time. Some people have genes that make them more likely to react strongly to certain vaccines. Others have genes that make them less likely to get certain cancers. These differences are often tied to recent changes in DNA, and they keep evolving as new diseases appear. Now, what about being left-handed? About 10% of people are left-handed. This trait runs in families, and scientists found several genes linked to it. The frequency of left-handedness is about the same all over the world. No one knows exactly why it sticks around. It might help with certain tasks, or maybe it's just never been a big enough problem to disappear. Let's talk about hair color. Red hair is most common in Scotland and Ireland. The gene for red hair is called MC1. It's a recent mutation, only a few thousand years old. It might be linked to how people handle sunlight, or just be a random change that spread because people found it attractive. Now, let's look at the future. With new technology, we can track how genes are changing. Right now, scientists are watching genes for disease resistance, height, weight, and even intelligence shift from one generation to the next. The pace is slow, but it's there. One last example: wisdom teeth and jaw shape. In the last few hundred years, as diets have gotten softer, jaws have shrunk, more people need braces or have teeth pulled. This isn't just a health issue. It's recent evolution responding to changing lifestyles. All these examples show one thing: evolution didn't stop when we started building cities or writing books. It's still going. Every generation, every new challenge brings new changes. Some are big, like the ability to drink milk or fight malaria. Most are tiny, like how you taste bitter foods or handle caffeine. The evidence is everywhere, if you know where to look. Our bodies are living proof that nature never stops tinkering. Every part of us, from our hair to our bones to our blood, is shaped by both ancient history and recent changes. So what does it all mean? It means we're not just walking fossils stuck in time. We're part of a story that's still being written. Every new environment, every new disease, every new food is another test, and the results show up in our DNA, one tiny change at a time. That's the real story of human evolution. Not a straight line, but a living, breathing process. One that's happening right now in ways big and small all around us, and sometimes in ways we won't even notice until the world changes again. When you think about evolution, it's easy to picture it as a slow, steady march, one step after another, little changes adding up over time. But the real story isn't always so smooth. Sometimes everything hinges on one accident, one twist of fate, one tiny change, and the whole path of our species shifts. Let's dig into those moments, the accidents that mattered. Not every change in our DNA is important. Most are just background noise. But every once in a while, a random mutation sticks around. Sometimes it's luck, sometimes it's timing. Sometimes it's just the world changing in a way that makes this one tweak the difference between life and death. Picture this. A small group of early humans huddled around a dying fire. Maybe a child is born with a slightly different gene. Maybe she's a little better at fighting off a new disease. Or maybe he can digest a strange new food that no one else can handle. Most of the time, these changes don't go anywhere. But sometimes they're exactly what's needed. Those are the accidents that matter. The ones that, for reasons nobody could predict, suddenly become the key to survival. Think about the history of our species as a long, twisting river. There are calm stretches where nothing much changes, but there are also sharp bends, rapids, waterfalls. Sometimes a single pebble, one mutation can change the flow forever. Let's look at some of those pebbles. Not the slow, steady changes, but the turning points. The things that, if they happen just a little differently, we might not even be here to talk about it. Here's where it gets interesting. Many of these big moments were pure chance. They weren't designed or planned. Hey, just happened, and stuck around because the world changed in a way that made them useful. Take the story of language. We covered the FOXP2 gene before, but let's go deeper. All humans today have a version of this gene that helps us speak. But here's the thing. This version is only found in our species. Neanderthals and other close relatives didn't have it. It looks like a single mutation, maybe 200,000 years ago, made it easier for our brains and mouths to work together. It didn't make language happen overnight, but it was like flipping a light switch. Suddenly, new kinds of sounds and words became possible. Imagine if that mutation never happened. Maybe we'd still be grunting and pointing, unable to share stories or ideas. Maybe art, culture, and history would look completely different. Here's another accident. The split between us and Neanderthals. Scientists think it started with a small group of humans leaving Africa, maybe 60,000 years ago. The world was changing. Ice ages, shifting climates, new animals. Some of these early humans ended up isolated. Over thousands of years, their DNA drifted in new directions. Most of the time, groups that split apart end up similar, but sometimes a few strange mutations pop up. They're rare, but if they help even a little, they can become common. That's probably how some of the differences between us and Neanderthals appeared. Bigger brains, different skull shapes, maybe even new ways of thinking. And sometimes these changes don't mean better, just different. If the climate had shifted in another way, maybe Neanderthals would have been the ones to survive, and we'd be the ones in the museum. Think about another accident, the loss of body hair. Most mammals have thick fur. Early humans probably did too. But at some point, our ancestors started losing their hair. There's no single answer why. Maybe it helped us cool off, ill running in the heat. Maybe it made it harder for parasites to hide. But the trigger was almost certainly a random mutation, a mistake in copying DNA. Once it popped up, it stuck around because it helped. At first, just a few people had less hair. Over time, the trait spread. Now, almost everyone has it. If that mutation never happened, maybe we'd all look more like chimpanzees than modern humans. Here's one of the biggest accidents. The mutation that let us walk upright. It didn't happen all at once. Our ancestors spent millions of years moving from the trees to the ground. But at some point, changes in the shape of our hips, spine, and feet made walking on two legs possible. These changes weren't planned. They happened by accident and only stuck around because they helped us survive in open grasslands. Walking upright freed our hands. Now we could carry tools, food, or babies. It changed everything. How we hunted, how we made things, how we saw the world. It set us apart from every other animal. But here's the twist. Walking upright also brought new problems. Back pain, hard childbirth, flat feet. The mutation was a trade-off. It helped more than it hurt, so it spread. But it wasn't perfect. Let's talk about another accident. The mutation that let us sweat so much. Most mammals cool off by panting. We sweat, and we do it better than almost any other animal. This might sound boring, but it's huge. It let us run long distances, hunt in the heat, and survive in places where other animals would drop from exhaustion. Again, it started as a random change. Maybe one person had more sweat glands. Maybe another had thinner hair. Over thousands of years, the traits combined. Now, we're the naked ape who can outrun almost anything if we're patient enough. Here's something wild. The mutation for larger brains. Our brains are much bigger than those of other apes, but big brain. Us, NS, are risky. They use a lot of energy. They make childbirth harder. So why did this accident stick around? The answer seems to be that big brains helped us solve problems, talk, and work together. The world kept changing, and those who could adapt survived. But the first step, the initial mutation for a bigger brain, was still a random accident. Maybe someone was born with a slightly bigger head, and it worked out. Big brains made us clever, but they also made us vulnerable in new ways. Babies with big heads are harder to deliver. Newborns are helpless for longer. Parents had to care for them. This probably pushed us to form tighter. Conclusion: we're all products of chance families, stronger groups. It was all connected. Now, think about thumbs. Not just any thumbs. Opposable thumbs, the kind that let you hold a pencil, tie your shoes, or text your friends. Other primates have thumbs, but ours are different. They're longer, stronger, and better at pinching. This change didn't happen overnight. It took millions of years. But each step was an accident, a small change in the shape of a bone or muscle. Each one made our hands a little better at gripping and making things. Eventually, we could make tools, throw spears, and build fires. If you're holding a phone right now, thank those ancient accidents. Let's not forget the accident of fire. Fire wasn't a gene, but it still changed us forever. The first time someone controlled fire, maybe by accident, maybe by copying lightning, it set off a chain reaction. Cooking made food safer and easier to chew. It let us eat things we couldn't before. It gave us light at night, warmth in the cold, and protection from wild animals. Cooking may even have changed our bodies. Some scientists think it let our jaws shrink and our guts get shorter. We could get more energy from a less food, which might have made bigger brains possible. All because someone somewhere figured out how to keep a flame going. That's the thing about accidents. They can set off waves of change that echo for thousands of years. Think about color vision. Most mammals see only a few colors. But somewhere in our past, a mutation gave us 3-color vision. Now we can see reds, greens, and blues. This helped us spot ripe fruit, find food, and maybe even read the emotions on each other's faces. This mutation happened before humans existed, maybe 30 million years ago, in a common ancestor of monkeys and apes, but it stuck around. It wasn't needed at first. But as the world changed, it became an advantage. Now, let's go back to the Ice Ages. The world got colder and food got scarce. Some humans survived because of accidents in their DNA. Maybe they could store fat better. Maybe they could handle cold better. These weren't planned changes. They were random, but they made all the difference. Fast forward to today, some people have genes that help them handle cold or heat, high or low places, fat or sugar. These are all accidents that stuck around because they helped in a certain time or place. If the climate had changed differently, maybe other genes would have become common. Here's a twist. Not all accidents are helpful. Some are neutral or even harmful. But sometimes they stick around anyway. Maybe they're linked to something helpful. Or maybe they just don't hurt enough to disappear. Sickle cell disease is one example. The gene that causes it is dangerous if you have 2 copies. But if you have just one, it helps protect against malaria. It's a trade-off. The accident sticks around because it's sometimes useful, even though it can also cause problems. Now, let's look at accidents that change society, not just bodies. Think about the invention of writing. It wasn't a genetic mutation, but it had a huge impact on who survived and who didn't. The first people to write things down could keep records, collect taxes, and organize armies. These skills helped their groups grow and spread. But here's the thing. If one accident in history had gone differently, maybe writing would have started somewhere else or not at all. Imagine a world where nobody ever wrote anything down. How would that have changed who we became? Think about the Black Death in Europe. In the 1300s, a disease wiped out up to half the population. Some people survived because they had genes that made them less likely to get sick. Those genes spread. Today, they're more common in parts of Europe than anywhere else. This disaster changed the mix of genes in the population. It was an accident. Nobody planned for it, but it shaped who survived. Here's another one, the spread of farming. The first people to plant crops and raise animals didn't know they were changing the world, but their children had more food, lived longer, and had more kids. Over time, their way of life spread. People who couldn't handle the new foods or diseases were left behind. It wasn't better or worse, just different. A series of accidents who tried a new seed, who tamed wild animal, who found a way to store grain for winter. Each step changed what it meant to be human. Let's talk about population bottlenecks. This is when a disaster wipes out most of a group, leaving only a few survivors. The genes of those survivors become the foundation for everyone who comes after. It's like shuffling a deck and only keeping a few cards. Scientists think humans went through one of these around 70,000 years ago. Maybe a volcanic eruption, maybe a big drought. Whatever the cause, only a small group survived. Their accidents became everyone's accidents. The traits that helped them, by luck or by skill, became the building blocks for later generations. This is part of why humans today are so similar. Even though we live everywhere, we all come from that small group of survivors. Their random mutations, good or bad, are part of us. Now, let's look at the accident of mixing with other human groups. We didn't just replace Neanderthals and Denismen. We mixed with them. Sometimes their genes gave us advantages. Genes for fighting disease, handling cold, or living at high altitude. These weren't planned. They happened because people met, had children, and their DNA got combined in new ways. Some of this DNA faded away. Some stuck around. Today, almost everyone outside Africa has a few % of Neanderthal DNA. In Tibet, people have Denisven genes that help them live in thin air. These accidents matter. If different groups had mixed or not mixed, our bodies might look and work very differently. Let's talk about the accident of migration. The first people to leave Africa did it for reasons we'll never know. Maybe they were following animals. Maybe they were pushed out by drought. Maybe they just got curious. Whatever the reason, that first step set off a chain of accidents. Some groups ended up in cold places, some in jungles, some on islands. Each new land brought new challenges. Only the people with the right mix of genes, luck, and skill survived. The story of Australia is a good example. The first people arrived more than 60,000 years ago. They had to cross water, face dangerous animals, and deal with harsh climates. The ones who made it had traits that let them survive. Over time, accidents in their DNA helped them handle sun, find food, and avoid disease. If a different group had landed, the story might have turned out another way. Now, think about diet again. Some accidents in our DNA let certain groups eat foods that others can't. The mutation for digesting milk is one, but there are many more. Some people can eat seaweed thanks to genes from bacteria. Others can't handle bitter or spicy foods. These changes often start as accidents. But if they help, they spread fast. Let's talk about the accident of immunity. The world is full of viruses and bacteria. Every time a new disease appears, some people die and some survive. Sometimes the survivors have a random mutation that protects them. Over time, these accidents add up. They shape who lives and who dies, who has children and who doesn't. Think about the recent pandemic. Some people got very sick, others barely noticed. Scientists are still figuring out which accidents in our DNA made the difference. Now, let's just step back and look at the big picture. The story of humans isn't a straight line. It's a series of accidents, tiny changes, lucky breaks, bad luck, and unexpected turns. Sometimes a single event, like a volcano or a new disease, wipes out most of a population. Sometimes a tiny mutation gives someone an edge. Most of the time, these changes don't matter. But every once in a while, one does, and when it does, everything that comes after is different. The world shifts, new possibilities open up, old wounds close forever. This is what makes evolution so strange and beautiful. It's not about perfection, it's not about progress, it's about accidents. What works, what doesn't, and what just happens to be in the right place at the right time. We like to think we're here, because we're special. But the truth is, we're here because of a million accidents. Some good, some bad, some that helped us survive, some that nearly wiped us out. If things had gone just a little differently, if one mutation hadn't happened, or one disaster hadn't struck, the world might be full of creatures that look nothing like us. Or maybe it would be empty. Every part of your body, from your eyes to your thumbs, to your brain, carries the marks of these accidents. Every step you take, every word you speak, it bazooks, shaped by things that once happened to people you'll never know. So when you look in the mirror, remember, you're the product of chance, of random changes and lucky breaks, of survival, risk, and the strange twists that make life what it is. And that's the real lesson of evolution. Not that we're the end goal, not that we're perfect, but that we're here against all odds because of the accidents that mattered. The ones that stuck around changed everything and wrote a new chapter in the story of life. Now, as we move toward the end of this exploration, let's ask, what does all this mean for us right now? What do these accidents say about who we are and who we could become? The answers aren't simple, but they're worth thinking about, even as the world keeps changing about us. Here's the thing about all these accidents, big or small, every one of them left a fingerprint on us. But when you step back and look at the whole story, it's not just a pile of random events. There's a kind of pattern, even if it's not always clear at first. What makes us human isn't just one change, one lucky break. It's the way all these twists and turns stack up, one on top of another, until you get something completely new. Think about it like a giant puzzle. Each piece is a little weird on its own. Some are rough, some are smooth, and a lot of them don't seem to fit anywhere. But start putting them together, and a picture begins to form. Sometimes the picture is messy, sometimes it's beautiful, sometimes it's beautiful, sometimes it just surprises you. So what does all this mean for us now? Are we just the sum of our accidents? Are we drifting through life, pushed and pulled by random events we can't control? Or is there something deeper that connects all the pieces? Let's look at what we can learn from our accidental history. First, accidents aren't always bad. Some of the best things in our story came from mistakes, surprises, and moments nobody could have planned. The first spark that became a fire, the first word that turned into a language, a strange new food that turned out to be safe. Each time someone took a risk or just got lucky and the world changed. But here's what's interesting. Humans are really good at turning accidents into something useful. We stumble on a new idea, and suddenly it's everywhere. We don't just accept change, we run with it. We make tools, build homes, paint on cave walls, and write down stories. Most animals react to change. Humans shape it. That's not just luck, it's something built into us. We notice patterns. We ask questions. We wonder what if. That drive to make sense of things, to turn an accident into an opportunity, is one of our best traits. Think about how we handle new problems. A disease appears, and we look for a cure. The climate shifts, and we invent new ways to stay warm or cool. We move, we adapt, we try again when things go wrong. Sometimes it takes a while. Sometimes a lot of people struggle, but over time we figure things out. It's not just about survival, it's about curiosity. We want to know what's possible. We look at a problem, and think, is there another way? That's how new ideas happen. Someone tries something odd, and it works, or it doesn't, but the next person learns from the mistake. And that's another lesson from our story. Failure isn't the end. It's part of how we grow. A lot of our accidents were things that went wrong for someone somewhere. But the survivors learned, changed, and moved forward. Each mistake taught us something. Here's where it gets personal. Every person alive today carries a mix of old accidents and new ideas. You're made from the DNA of survivors, people who faced hard times and kept going. But you're also part of a world that keeps changing. New challenges, new chances. So if you ever feel like that's out of your control, or if you worry about making mistakes, think about all the accidents in our past. Most of them weren't planned. Most of them looked like dead ends, but some of them turned into the best parts of our story. Nobody knows what the next accident will be. It might be something small, a new food, a strange idea, a tiny change in how we live. It might be something huge, like a new invention or a big shift in the climate. We can't predict every twist, but we can pay attention, stay curious, and look for ways to adapt. And that's where hope comes in. The story of humans isn't just about surviving disasters. It's about turning the unexpected into something better. We build on the past, but we also dream about the future. We ask what's next. Sometimes we even make our own luck. That doesn't mean everything will go right. Some accidents hurt. Some changes bring problems we never saw coming. But we can learn. We can look for patterns. We can help each other. It's easy to feel small when you think about all the accidents that led to now. But you're not powerless. Every person adds a tiny piece to the story. Every choice, every risk, every new idea is a chance to shape what comes next. Think about how fast things can change. 100 years ago, the world looked completely different. 200 years ago, almost nobody had electricity, cars, or phones. Now you can talk to someone on the other side of the world in seconds. All because people kept trying new things, sometimes by accident, sometimes on purpose. And we're still changing. New accidents are happening all the time. Some are in our DNA, some are in our culture, our technology, our ideas. The world never stands still for long. But here's a gentle reminder. Change doesn't always mean rushing forward. Sometimes the most important thing is to pause, to look around, to notice what's already here, the people in your life, the things you've learned, the little day surprises that make each day different. Maybe that's the real lesson from our story. Accidents will always happen. Some will shake the world. Some will barely be noticed. What matters is what we do next, how we respond, what we build, and how we care for each other. So when you hear about a new discovery or a problem nobody solved yet, remember this is how it's always been, a chain of accidents, lucky breaks, tough times, and new beginnings. And we're all part of it. You're living proof that the world can change in amazing ways. Every breath you take, every thought you have, is a result of billions of years of twists and turns. Some of those changes were scary, some were beautiful, most were unexpected. If you ever wonder about your place in the world, just remember you're the outcome of a long, wild story. A story that's still being written. You get to add your own chapter. Maybe it'll be a big change, or maybe just a small kindness. But it matters. And when you face your own accidents, your own surprises, remember how much good came from the accidents of the past. The things that seemed random, strange, or even unlucky have shaped everything you see and do. So, as you move through life, stay curious, keep asking questions, try new things, even if you're not sure how they'll turn out. The world is full of surprises, and you never know which one will make all the difference. In the end, we're not just a product of accidents. We're also the ones who notice, learn, and dream. We're the ones who turn the unexpected into something meaningful. That's the real power of being human, and that's what makes our story worth telling again and again.